Well, good morning.
Good morning, sir.
Good morning, sir.
Hope we are fine.
By His grace, we're doing well.
Thank God. We couldn't go to church. Is there a pastor among us?
This course,
Because of this course there, our church going has become
this course.
tremendous. So
Oh, I'm telling you.
now we can't go to church because
Yeah.
of this course. But I even see my parish priest.
Your
I'm
shoe.
running away. I see my parish priest, and I'll be running away.
Oh,
Hmm.
yeah. It is something, but maybe, 5 to 6 weeks time, everything will come to an end.
True.
Okay. I think yesterday we were around 19, but we are 12 now. Means that 7 people are missing. So let's give ourselves some 5 minutes in addition. Because already we waited for 10 minutes.
Please, is it being recorded? Have they started?
Yes, I heard it.
Yeah.
I heard that they have started recording.
Okay, so if any of you is touched by the Spirit, to pray for us and then start.
But please, we are praying. Our Heavenly Father, we thank you this morning for giving us another day. Father, as we come gather here to study, it is our prayer that everything ends successful. It is our prayer that, Father, you let your angels and the Holy Spirit guide us throughout this course. And at the end of the day, if you are successful, and we know that we will be successful in the name of Jesus, we pray. Amen.
Amen. So if you are not successful, you will not pray to God again.
And I know you will be successful.
But the Bible says that
That's
in
the question I
everything
was
we
going to
should give
ask.
thanks and praise to God,
Sure.
regardless.
Okay. Thank you for your wonderful prayer. Yeah, so today we are starting with classical mechanics. Classical mechanics is also a continuation from Newtonian mechanics. So the Newtonian mechanics, we're looking at the motion of objects using the Newton's laws of motions. So the Newton's three laws, that was what we used to describe Newtonian mechanics. So the new thing that we are adding to this concept is that we are using other two laws in addition to the Newton's laws that we know. So we can say that this is a post-Newtonian mechanics. So we'll be looking at, after the three Newton's laws of motion, then we'll look at what we call the Lagrangian and then the Hamiltonian. And the concept is still the same. So we want to use these laws to also see how objects are being moved. So in other words, to describe the motion of the object, the velocity when force is subjected to the object. So basically, that is all about classical mechanics. So we are still going to revise our Newtonian mechanics. Then we add the other two laws. Okay. So
Hello, sir. Good morning.
yes, good
Morning,
morning.
sir.
Good morning.
Yes, I was going through them, but then I see that this course is very much related to the electronic, this one, electromagnetic field. That
Electromagnetic.
is some most of the concept. Yes, so I was wondering why maybe one person.
Magnetism.
No, not magnetic. We are also doing electromagnetic field. This image.
Yeah, electromagnetic field.
And so that it is very much linked, like most of the concepts.
Maybe because you saw vectors, that's why you think it is
So
like, you know, in physics, whatever we are describing, once we are talking about motion, we don't forget about vectors. And so that's why
that's why
you see
that's why
most of the courses that we are doing, once it is motion, you have to wake up on your vectors. Okay. So is there one unit or an aspect that is like similar to what you say, but the dynamics is not going to be the same thing. Okay. So you see vectors. That's what I said. You know, Newtonian mechanics, we learn about vectors. We also revise vectors here. We'll revise our Newton's three laws of motions that we learned in Newtonian mechanics. Then we will now proceed with the other things that has been added to make it as a different course from the Newtonian mechanics. So as a matter of fact, all the courses that we are doing, they are interrelated in a sense that there are certain things that.
I'm saying that because, okay, maybe if I may go straight to the point, you write a lot. So I'm hoping that I know you'll be writing now. You've made this one available. I beg. I said the one who will be teaching us the other course. I beg. It's not that I'm imposing. If you can also be doing a lot, small writing, it will help. It will help because you can't think physics is not a reading service. It's not comprehension. So I beg, if that's why I was wondering, since they are linked, you can be doing both for us, but since a different person will be doing it, you should write a lot. It's not that it be comprehension, then you'll be reading, then we'll like that. It doesn't help at all. That you see that now you've made the feed available, you write. It helps a lot. You can't listen it like comprehension, English comprehension. Thank you.
Mr. George, but you can politely, suggest to him, since you are aware that he's the one taking us.
Okay, I think let's finish with our class and then maybe
it's not I'm imposing.
We can discuss it later on. Okay, so as I started saying, we know what motion is. When we talk about motion, we are looking at the relative movement of objects with respect to time. So mechanics is about motion or how objects are being moved. Then this mechanics is being put into two categories. So the first one, we talk about the kinematics. So for the kinematics, you are looking at the motion of the object holistically. You're just looking at how the objects are moving. Then the second part has to do with the dynamics. Then with the dynamics part of the mechanics, you are trying to figure out what is the cause of the motion. Okay, so in other words, you want to look at the driving agents, which is the force. Okay, so we will look at the meaning of the subject, which we are calling the classical mechanics. So you can write that mechanics is basically a branch of physics. So this is a branch of physics. Okay, that describes the motion. That describes the motion, into brackets, kinematics. And the cause of motion, and the cause of the motion. So the cause will be looking at the dynamic aspect. So dynamics. Okay. So as I mentioned earlier, the dynamic aspect will lead us to the forces, because we want to look at if there is no external force being subjected to the object or the system under study, what will happen? And when you're just trying to look at how the particle is moving without thinking about what is causing it, that has to do with the kinematics. Now, this is about the behavior of physical objects when subjected to force or displacement. So in general, what we would say is that it deals with, so mechanics deals with a set of physical laws describing the motion of bodies under the influence. So under the influence of the systems of force. Okay, so that is the definition for mechanics. Okay, so now there are four basic ways that we can place this mechanics into. So let's say 4 categories. Mechanics can be identified. So based on the size and the speed of the objects. Okay. So what we are trying to say here is that the way and manner a microscopic system or object will move will be different from how a microscopic system will move. So though they are all dealing with or talking about movement of objects, but the description that you will give to a minute object may not be the same thing as that of the micro objects. Okay, the concept is going to be the same thing, but there will be a thing different between them based on their sizes or the speed at which they are moving with. So later we have these categories of the mechanics. We have the quantum mechanics. So we have one, we have the quantum mechanics. They are all mechanics. Two, you talk about the classical mechanics, which is the course we are doing. Then three, we talk about relativistic mechanics. Then lastly, we will talk about the quantum field theory. Okay. So all these three different type of mechanisms that you are seeing, they all describes motion of object based on size and then speed. So we talk about their sizes and then speed. In other words, the mass and then the speed. Okay, so if you want to now place these four mechanics that we have seen in a graph based on size and speed. So this is our size, then this would be our speed axis. So we'll have a graph like this. So here we have the size, the average diameter of an atom, which is 10 to the power minus millimeter. Then add this one. So therefore, okay. So you have a quantum mechanics being reciting here. Here we have quantum mechanics. Let me use Qm. So this is 0. Then we have the field theory. So I will use QF here, QFT for quantum field theory. Then relativistic mechanics, so RM. Then lastly, we have our classical mechanics here. So this is telling us that if you are looking at a very, down the y-axis here, the size axis, the size of the object you are looking at is very small, because if you are going down, so it means that from 0, you are increasing small. Okay, so increasing up. So within this range, it means that you are looking at a minute object. So a particle that has a lower or lesser mass with what? A lower speed. Now, when you move to quantum field theory, you see as moving to the right, the speed is increasing. So here you are describing particles that are moving with a high speed, but with a very small mass. Now, when you come to the classical mechanics as we are doing, then that one you are concentrating on objects that are having larger masses at the same time, a very small velocity. So we are looking at objects that you can see, and then these objects are moving with a speed which is far less than that of the speed of light. The speed of light is the reference value when you are comparing velocities to. So you expect your object here to move with a very small velocity. Then the relativity mechanics, that one also deal with a high-speed object, but with a very large mass. Okay. So these are the four forms or categories of the mechanics that we have. So what classical mechanics now aim to do is that classical mechanics aims to describe the motion of macroscopic object moving with speed far less than the speed of light. So that would be our focus. So we will be looking at this, then microscopic. That is larger size object with a larger size or mass. So let's look at as I said, the Newtonian or post-classical, so you can change them. Classical theory generally valid when they are describing low speed objects, low speed into bracket, that is being compared to the speed of light. Okay, so if you are dealing with anything outside this, it means that you will be talking about the other aspect of the mechanics, not the classical mechanics. So let's see where these laws are breakdown. So the breakdowns of the Newtonian or classical mechanics, or in other words, where we can no longer use the Newton's laws to describe the motion of the particle. So the breakdowns. So breakdown of Newton's laws. So the first breakdown is that it breaks down, or in other words, it cannot be used. So that is the meaning. Either it breaks down or it cannot be used. So it breaks down, and it's right now 10 legible so that you can. It breaks down, and it's being replaced. And it is replaced by Einstein theory. Einstein theory of relativity. Theory of relativity for object moving for objects that are moving with a speed approaching that of the speed of light. Okay, so when you are talking about an object that is moving with a very high velocity, then classical mechanics sees to explain that you have to use the knowledge of Einstein theory of relativity to explain that object. So it means that in short, you can say that Newtonian mechanics or classical mechanics doesn't work for a high-speed object. So that is one of the breakdown. Then the second breakdown you talk about is that in the atomic scale, so when you are also dealing with particles that are having low mass, so you can also use classical mechanics or the knowledge in classical mechanics to do that. You have to also use the idea of quantum mechanics. Okay, so that is another thing. So two, the second breakdown is that it is also breaks down at the atomic scale level. So at the atomic scale, and it's being replaced by quantum mechanics. So that is within the domain of classical mechanics. The system should be this. So in other words, you can say that in other words, within the domain so let me put CM so that we know directly of classical mechanics. Within the domain of classical mechanics, you can say that one, the system should be isolated. And two, can also say that the system should be non-relativistic. Should be non-relativistic. That is, it means that the speed of the system should be far less than that of the speed of light. So the V is the speed of the system that you are studying, and the C is the speed of the light. Then finally, you can say that the system should be non-quantum. Should be non-quantum means that that system under study should have a size that is greater than the average diameter of an atom. So the size of the system should be greater than greater than the average diameter of an atom. (10⁻⁹) nanometers. Okay, so these are the three things that you should have in mind when you are describing anything in classical point of view. Okay. So let's now look at the concept of Newtonian or classical mechanics. Okay, so what is it based on? There are four concepts that we need to take into consideration. So there are four. Then, so the main concept, there are four, and we have one. We have to talk about the space. Then two, we talk about time. So space has to do with position of the object. So position, talk about point object or point that is located. We have to talk about the direction under the space, and then finally we talk about displacement. Then the second is the time frame. Look at the time frame. Then we talk about the mass, that's the size of the object. Then finally, we talk about the forces that are causing the thing. So we cannot describe classical mechanics without putting these four concepts into or together. So we will first of all look at the space. So I pick the space, and as I indicated, the space has to do with the particle location, the displacement, the direction, and then the point. Now, what is space? Talk about space is just a measurement that involves the concept of length. Okay, so how does, or what is the magnitude of the object that you are talking about? What is the length of the object? In other words, are you looking at the object in 2 dimensions, 3 dimensions, or in a 1-dimensional manner? So is the particle moving linearly or it is rotating? So all these things must come in when you are looking at the motion of the object. So the space has to do a measurement in space involves the concept of length or distance. And then is it a 3D plane? So 3D mean dimensional vector. Okay. So that is So now you have to, so if you are doing that, means that we have to revise on our vectors, just as I mentioned earlier. So whatever we learned previously, we need to revise them before we now add the new concept that is there to it. So on the mentioned vector, you talk about the direction and then the magnitude. So a vector is identified and represented and is represented by this in the component. So we have the X, the Y, and then the Z direction. Is chosen. These are chosen perpendicular axis. Okay, so we can't do without looking at these axes. And this is expressed by introducing the 3 units. Vectors. So these are the 3 unit vectors. So we have X cap, we have the Y with the cap, then we have the Z, the cap. So we all know how to write a unit vector. We know what a unit vector is. A vector divided by its magnitude is what we call a unit vector, or a vector with magnitude of what? 1 is a unit vector pointing along the 3 axes. The 3 axes. Okay. So now we can write a position vector. So a position vector means a location of the particle. You know, when you talk about the space is just like an opening. So when you raise something above the ground level, so you presume that that object is what? In a space. And once it is on that height, you have to describe the direction based on the 3 dimensions. So it will have both X, Y, and Z that the dimensions. So if you want to write the position vector of an object, position vector R, so with the arrow bar, is therefore expressed as this. So the vector R will be equals to xi plus yj plus zk. Okay, so this will be a vector depicting the location of an object where the ijk, ij, and k are unit vectors. Unit vectors. So, in short, you just the space talks about the particle location, and that is where you need to apply your vectors. So, if we have a particle that is being represented in the XYZ plane, so this arrow, so we have our 3-dimension. So this is our Z direction. This would be our Y. This would be our X. Now the unit vectors are I, J, K. Now, let's say we have a vector which has a unit vectors on both axes. You want to find the location. So let me put my particle here. So the location of the particle is in this space here. Okay. Oh, yes. So what you need to do is that if you are having like a vector 1, 1, 1, so it means the vector has magnitude in both axes 1, 1, 1. So we will move 1 unit along the x direction like this. So assuming this is calibrated, we have 0 in the middle, then we have 1 somewhere here, 2 in that order. Then we come down to the 1 unit, then we'll move along the y 1 unit, then we have to move up. Okay, so moving up 1 unit will also be here. So it means that the particle will be around this, but I just want to locate the particle here. So let's say we'll have to go down, then we'll go parallel to the y-axis. Parallel to the y-axis, then we move up to where the particle is. Now, from that point to the origin will now represent our vector. So this is now going to be our vector up this side to the origin. So this will be vector R. Okay. So that is how you represent. So we can put this point as P. So P is the point from the origin to P. So we can talk about the vector operations. So the vector operation has to do with vector addition, vector subtraction, multiplication, and then what? Division. That is the vector operation. So when you have more than one vector, how are you going to add the 2 vectors together? When you are adding them or when you are subtracting them, how do we do that? So this one is not something that we should waste time on. It's just like something we need just to look at vector operations and then we move on. So you talk about the addition, the scalar product, then the vector product. Okay. So let's say we have 2 vectors. if we have two vectors, let's say vector A and then vector B with their corresponding components, then we want to sum the two vectors together. It's just going to be vector A plus vector B. Okay. So let me say the addition. So it means that we are dealing with operation of addition. So let vector A is equals to the component AI or A1. You can define it any other way you want. So let me just say A1 I maybe plus A2J. Then B is also equals to B1 I plus B2J. Now, since we are dealing with the operator addition, so if I want to find vector A plus vector B, that is going to be A1I plus A2J plus BI or B1, sorry, B1I plus B2J. Now what we do is that we add values that are in the same direction. So if I have A along the X, then I have B along the X. So I'll add the coordinate that has similar values that are in the same axis, components in the same axis together. So I'll add the X values and also add the B values together, the Y values together. So here it means that if you look at the unit vectors, we have I's and then J's. So I'll put the I's together, also put the J's together. So this is going to be A1 plus B1, all with the unit direction I, then plus A2 plus B2, all with the unit as J. So this would be vector A plus vector B. So if A and B are numerical values, then you simplify. So assuming A is maybe 5, B is 1, B1 is 1, so you simplify. So one thing you should know is that when you add two vectors together, the result is also a vector. So that is for the vector addition. Then we talk about a scalar product. So scalar product is multiplying two vectors together. So the other operation will be the scalar product of a vector. Scalar product of a vector. Now here, if you have the same example, so we have vector A and vector B. So let's say go back by our example. So still our vector A is equals to our AI plus or A1I plus A2J, and then the B is also our B1I plus B2J. Now to find the scalar dot product of these two vectors, we'll have vector A dot vector B. So this dot sign is indicating a multiplication. Okay, so that is going to be equals to A1I plus A2J, all is dotting with B1I, and then B2J. So this will now give us A1, B1 plus whatever you have. So you are dotting the same way i's together, because you know I dot I is equals to j dot j, which is the same thing as k dot k, and this will give us 1. So I dot j is the same thing as j dot k, which is the same thing as k dot I, and this will give us 0. So for the dot product, you are dotting similar thing together. Any other thing that are not in the same coordinate, you get what? 0. So we're going to have A1, not AI, A1. So we take A1, B1. Then I dot I will give us 1. So any number times 1 is the same number. Then plus, if I take A with B2, because of the I and then the J, it will give me 0. So we are saying that when you are dotting two different unit vectors, unit vectors, it gives you 0. So here we have I and we have J here. Because they are not the same, you get 0. So the term goes to 0. Then we come to the next second term in the first bracket. A2 dotting with, this is J, dotting with I, we give you 0. Then A2 with B2JJ. So this will give us A2, B2, and then J dot J will give us 1. So this will be the expression for vector A dot B. And this is what we call the scalar dot product. Now, depending on the nature of the vector, whether the vector is inclined at an angle, then you can write it to find the acute angle. So in that case, we can have A dot B is equals to A magnitude, B magnitude, cos of the angle theta. That is if the vector is inclined and you want to find. Then if it's about cross, so A cross B, vector A vector B cross will be equals to same A magnitude, B magnitude, then we now have what? The acute angle to the sine. So this is a vector cross product. Okay, so you can find the magnitude of a vector. So magnitude of a vector, as we know that a vector is a quantity or a scalar quantity which has both magnitude and direction. So if you pick vector A and you want to find the magnitude, you want to find the magnitude of that vector. Magnitude of A. So that is going to be, we put it in the absolute bar, the root of the component A1I square plus A2J square. So when you find the magnitude of a vector, you expect a number. You don't expect a vector. So what it means is that here you have to square the number, then the unit vectors will be also squared. So if I have I square, that will give me I dot I, and this is going to be 1. So at the end of it all, this should be simplified to a number. So that is what we can talk about. Okay, let me start at the vector product or the cross product. So when you are also given two vectors as A and B that are used, you want to find the cross product. So you put them in a matrix form and then find the determinant. So vector A so A is the same thing as A1I plus A2J, and B is also B1. Because of the field theory, you also need this one, B1I plus B2J. So now for me to find A cross B, I'll put these two vectors in the matrix form and then determine the determinant of it. So that's going to be A. So first put the unit vectors. So I'll have I, I have J. So this is a 2 by 2 matrix. So I have A, then I have A1 here, then A2, then I have B1, then I have B2. You write it in terms of their units. So when you come to A has a direction of what? I. So that's why I've written A1 in line with I. B1 is also having a unit direction of I. So you write it down there. When I come to A2, it has a unit of J. So it should be here. So don't make a mistake and go and write it like I here and then write A1 and A2. No. So we find the determinant of this. Now the determinant is found by using the diagonals. Okay, so this will multiply this minus this by that. So find the determinant of that, and that is going to be, so A cross B is going to be equals to, so I have A1, then multiplied by B2. B2 minus A2 multiplied by B1. So since this is a 2 by 2 matrix, it's just simple to read. But if you are dealing with a 3 by 3, that is why you need to take into consideration of the sign. So if a 3 by 3, then you have a K. So you have positive, negative, then positive. You have to add this to it so that you can know that your J value is always negative. Okay. So this will be the vector product of the matrix. Okay. So that is all about the space. Now let's come back. We'll come back to this. So this is an introduction to vectors. So when we are now coming to find velocity, momentum, and that, we'll be using these things because we know that a velocity is a vector quantity, momentum is a vector quantity. So now let's also talk about the second concept that we talk about, that is the time frame. So time, this is a single universal parameter. So time is a parameter on which all observers agree on. Agreed, provided all observers of an event are equipped with accurate. Okay. So we are saying that time is a universal parameter, or is a parameter on which all observers agreed on, provided all the observers of the event are given an accurate and properly synchronized clock. So what we are trying to say here is that, so we are all in our various places. But if you check on our clock or our time, whatever time you have it there will be the same thing I'm having here because our times are correctly set. Okay. So if you are describing something, maybe we are more than two people that are watching the behavior of something. So once you synchronize your watches and they are correctly set, then whatever information you will get relating to that thing, as far as time is concerned, will be the same thing as the other observer. For instance, you want to monitor how fast a car can move. Maybe let's say, forget about the nature of the road and whatever. Let's say all those things are being kept in place, and you want to see what is the average time that a car can move from here to Accra. Let's presume no traffic, nothing is there, no speed ramps. Then if one is at the starting point, then the other one is at the end point, and you all start together. So by the time the person leaves at your end, when he gets to the other person's place, then all of you are expecting to pronounce the same time. So that is what we are saying, that it is a universal parameter which all observers agree on, provided that they are given a proper synchronized time for watches. Now, in the domain of classical mechanics, speed are much lesser than the speed of light, as we saw earlier. And therefore, there is a difference in measuring time. Okay, so the different measuring time is always negligible. So we can add, so in the domain of classical mechanics, speeds are much less than the speed of light. And therefore, the difference along measurement measure time, sorry. Measure time is not measurement. Measure time is negligible. Okay. So that is about time. Now let's look at what we term as frame of reference or reference frame. So reference frame. Reference frame, or you can pronounce it frame of reference. Okay. Now, this is the framework. Here's the framework of special space. It's a spatial origin. Look at a spatial origin and axis. And axis to label position. To label position and a choice of temporal origin. Choice of temporal origin. So what we are saying here is that okay, to measure with time, and then to measure time. Yeah. Yes, Mr. George.
So please, is there a difference between spatial and spatial? Well, here in the book, you said that it is it's a spatial. This spell it at
S
SPACIAL. Always
S what? S.
SPACIAL. Spatial.
Come again with the spelling.
SPACIAL.
C. Yeah, that's how I spell it.
No,
So you spell it spatial.
Mr. Festus, please, he's trying to emphasize on T rather than C. I think spatial.
Yeah.
T as in telephone.
T. Okay. Here.
Yes. So they spell it.
Okay.
No, so I'm saying, are there any difference or they are the same?
It's space.
Yes, space.
So it's spatial. So what it means is that, when you talk about a frame of reference or a reference frame, you are taking that place as your origin. So let's say you have two things, an observer, somebody who is standing by a roadside, and then a car passes by the person. So you that is standing, you will see that is your frame of reference. So you are taking the measurement from your origin or your position to the person that is in the car or moving. So you will see that, okay, in my frame, I am not moving, I am stationary, but the car that is moving. Then once you are also in a car, you presume that the car is not moving, but is that person that is also moving away from you. Or at times when you are in the car and then you bypass somebody, it's like the person is moving backwards and you are not moving. So that is the meaning. So it's a space. So where you are taking as your point of reference. Yeah.
Okay. So it is C and not.
Festus, the spatial and the spatial, okay? From what I just read, they're saying that the spelling is spatial, but the spatial is used less often and sometimes it's incorrect. So the main spelling is spatial, but you can also use the C.
Spatial.
Yeah, the main spelling is the T, but you can also use the C. But normally in formal writing, the C is incorrect. That's what they are saying.
They're saying, okay. All right, then that's fine. So special. Okay, so that is the frame of reference. So we have two types.
Sir, please, so the explanation for spatial references The
Mhm.
reference frame is like where you take as your origin or
Yes.
where you are relative to a moving object.
Yeah. So it depends on the origin, where you take it at the origin. So that's why we say that it's going to be a temporal origin. It's not like something that is permanent. So like if you are measuring something from 0 to 10, so you can start from 0 as your origin, then you measure up to 10. The same way, someone can start at 10 and measure backward to 10, and you still have the same magnitude. You understand? So wherever you want to take it as your origin, so that is your frame of reference or your starting point. Is that okay?
Okay, thank you. Okay, thank you.
Yeah. So there are two types. So two types of frame of reference. Two types. So we have one. We have the initial reference frame or frame of reference. And then the second one is the non-inertial. Inertial frame of reference. So when you talk about inertia, what does it mean?
You can describe as the unwillingness of a body to move,
Okay,
or
so
it can be
it talks about mass. Yeah,
The tendency to resist motion, sir.
okay.
or say
Well,
can you also, or when it is moving to, it will be unwilling to stop. So if it is moving, it wouldn't want to stop. If it is stop,
at
stationary,
rest,
it really want to move.
yeah, that's it. So that talks about the Newton's first one. Okay, so these are the two types of frame of references that we have. So let's now see their meaning. When you say an initial frame of reference, what does it mean? When you say non-initial frame of reference, what does it mean? For the initial frame, so let's say the initial frame is the same thing. You can be frame of reference or reference frame, whichever way you want to write it. So this one means that the frame is non-accelerating. Okay, we are talking about in a frame where the objects are having zero velocity, and then within that, all the three laws of Newton valid. So you can say an initial frame of reference frame is a non-accelerating frame in which the basics laws of physics. So in the basic laws of physics, such as Newton's laws, holds in their standard form. Their standard form, sorry. So that is for the initial frame. Then when you also talk about the non-inertial, so it will be in the opposite. So for this one is the one in which the system is what, accelerating or rotating. So know the difference. The one with the non rather has an accelerating system, but the one that is just a normal inertial frame of reference, that one we presume that the system is at rest. So non inertial reference frame is one that is accelerating or rotating. So in this frame, we put it this way. So in this frame, Newton's laws do not hold. Newton's laws do not hold. So all inertial frames are now like this. All inertial frames are a state of constant rectilinear motion. And are not accelerating. Okay. So that is it about the frame of reference or the reference frames. So let's now look at the Newton's laws. Okay. So we know that Newton is the father of mechanics, and he proposed 3 laws when it comes to motion, and these laws are there. It cannot be disproved. What he has said is final. Because,
Please, there are a lot of hands up.
hey,
Please, it's from your side, though. It's from your side. Everything is clear here.
There's nobody here, sir. I'm just the only one.
No, I said a lot of hands up. People have raised up their hand.
Okay,
okay. Oh, sorry.
And that's sorry.
I thought you said noise. Oh, okay.
I also heard noise.
Kindly ask the question, please. No, I'm not writing on like the interface where we joined. I'm writing on the PowerPoint itself. So unless I hear an alert, if you raise a hand and I didn't hear it, you can just prompt. Yeah, go ahead and ask the question, please. George.
Okay, so I said if you can go back to the previous thing you wrote, please.
Okay.
I was trying to write this, but you said one of them does not obey. Is it the non-elastic? It's a non-inertial reference.
Yeah.
It's one that
is accelerating.
Yeah, he said this frame does not be Newton's law does not hold, and I want you to put a little light on it. That particular point, you said with this frame, Newton's law does not hold. The last part in this frame.
Okay. So when the frame is also moving, that one you have to be thinking about relativistic physics. So one moving relative to the other. So you have both frames in motion. So in other words, you are no more having an origin again. And so you can't use the Newton's laws to describe that motion. So you have to be thinking about another concept, and that will be moving you to relativistic physics. But for the initial frame of reference, we presume that the system is not moving. The system itself is not moving. We're just looking at, not like we don't take it this way that like any particle that is in motion, Newton's law cannot be used to describe. No, that's not the case. But we are thinking about a frame, not just as an object. So the frame is your locality, okay, your area. So once the frame itself is moving, so for instance, if you take the world itself is moving, and then all the things within the world are also moving. So we cannot rely on Newton's laws to describe that movement. We have to shift our thinking to a different concept. But when we presume that the world is stationary, the things that are inside the world that are moving, but the world itself is stationary. Okay, that is like what we presume. You know, the earth moves. The earth moves, but its movement is not as fast. And so you presume like it is stationary. But at the same time, you have a car moving in the earth, and the earth too is also moving as fast as that. You can't use the Newton's laws. So that's why we are saying that Newton's laws do not hold in that frame.
Okay, sir. Thank you.
Yeah. Welcome. Any other question? Okay, so we can proceed, right? All right, so what are the laws of Newton? The first law. So first of all, look at the first law. So Newton, first law.
The first law said that
Okay.
a body will continue to be in a state of rest, or if moving, unless acted upon by an external force.
Is that all?
Yes, please.
Well,
A body will continue to be in a state of rest, or if moving, or like either in a state of rest or in a motion, unless acted upon by an external force. So if a body is moving, it will continue to move. Or if a body is in a state of rest, it will continue to be in a state of rest unless an external force acts on that body.
Why defining this way, they'll mark you wrong and you will not understand why you were marked wrong. Yeah, you said if a body is at rest, it will continue to be at rest, right? And when it is also moving, it is continuing to be in motion unless acted upon by an external force. So unless acted upon by an external force. So does it mean that an external force cannot cause a body at rest to move? It can. A body that is also moving, when the external force is acted on it, can also bring the body to a rest. So you have to add the condition to it. So when the external force is being acted upon that body, which is at rest, can change the direction. Once you are at rest and then there is a force subjected to you, you will move. That's why when you are standing and somebody pushes you, then you move. When you are moving and then you apply a force, you stop. Like when you are driving, you apply a brake to your car. It's an external force that you are applying to the car. The car comes to a stop. You can change direction, you can change the velocity. So when you bring, unless acted upon by an external force to either change the speed or the direction. So you have to complete it that way. But if you define like that, you like an external force does not have, if the body is at rest, it cannot cause it to move, or if it is also moving, it cannot do that. You have to complete it that way. Okay, so that's fine.
But I said, Festus, I mean, yes. a body can either change direction or speed if only that body is moving. But once you are at
no, not if only it is moving. You can change your direction when you are standing. Assuming when you are standing, what is your direction? What is your direction when you are standing? Let's just forget about where your face is moving, or your face is facing.
Yes. So maybe if you are facing, when you are standing, you are facing north. Definitely, you can change your direction to face east.
So what would tell you to change your direction? It's not a force.
Yes.
So he shouldn't say that the body can only change direction if it is moving. You can rotate. A car can stand and rotate and change the direction. What is causing it to change the direction? It's a force. Are you getting me, my brother?
Please,
yes.
I beg to differ. A body which is stationary cannot change its direction.
A body which is stationary.
Which direction is the body moving? As Castro was talking about when you are facing north. If I'm facing north and someone really push me at the front, I'll go back.
You will go back.
I'm not having any direction now when I'm stationary.
It can cause you to change direction.
But you've forgotten that you can rotate.
It's the force that can cause me to rotate or can cause me to move to the direction of the force.
That
Yes,
is
so that's
exactly what he's saying.
But
That's
no,
exactly what he's saying.
no. What you are saying is that I have a direction, and being stationary, a force can cause me to change my direction. That's what I don't understand.
But that's what he also said.
Did you hear his argument? He said a body can only change direction when the body is in motion.
Yes.
That is what he's saying. And I'm also saying that when a body is at rest, and then you subject the force to the body can rotate and change the direction. Please, your microphone is making noise. If you can mute yourself.
Sorry.
Ben, I think it's yours. Ben.
I'm coming.
Someone.
Sebastian, can I make an example?
Yes.
Okay.
Per my analogy, a body must start moving before it can change direction. A body cannot be in a state of rest and direction change.
I think it looks like you are not getting me.
Per the definition I said, a body will continue to be in a state of rest. So if I'm at, like now I'm sitting down here, I'm at rest.
Yeah, I can.
Unless external force acts on me before I can move. And if I'm moving too, or if I'm in motion too, without external force acting on me, I'll continue to be in a motion.
So, well, that is right. But if the external force is acted upon you on your opposite direction, will you change direction or not?
As in a state of moving or rest?
It's stationary. EB, let's look at this. Have you seen dragging? A car dragging?
Yes.
A drag of a car. Second, on the front tires, no, on the snake, air trying to like it is going round and round, like in a circular form. Have you seen that thing before?
Yes.
In movies.
Yes.
Good. So the car will be at rest. Okay. But immediately an external force is acting on it.
It changes the direction.
It's not moving, no. It's not moving. The car itself is not moving.
But even let's say that.
I just
let's say that
so the external force is causing it to what? To rotate, to change direction, but it's not moving. Does not move from the force.
You park your car and somebody comes to knock your car. What will happen? The car, let's say the person knocks at the tail end of it. The car will rotate, but that car was parked, wasn't moving. So once it's knocked, it will change the face of the car or the direction of where the car was moving. So,
but it will not move. It will still be at rest.
The car was at rest before the external acted upon it. And then again, a car can also be in motion. And when the external force also acts on it, then it changes the direction. Are you getting what I'm saying? Did you get it now?
I think we should continue.
Yeah, so that is it.
Hello. Because when the car is rotating, it's moving on a circular motion. And that car was at rest. So when the external force acting on it, is the external force who is causing the car to move in the direction of the force. So
that's what we are saying.
If it is stationary, the car is not having any direction. So external force cannot change the direction. It's the external force who is going to cause it to take a direction.
My brother, I think like you just want to argue. When the car is parked, it has a direction. Where is the front of the car facing? When you are standing, where is your face facing? You have a direction. You are facing north, east, or west. So don't say any stationary object has no direction. It's just that maybe probably you want us to drag this as an argument.
Oh no, sir. So, sir, what about if it is a stone?
Festus, please let me ask Ben. Ben.
Yes.
Ben. Okay, so you are saying that a stationary body has no direction.
Yes.
And an external force causes it to move to another direction. Hasn't it changed direction?
From where to where?
From zero to the new direction. You are saying that it has zero direction.
If it is zero, meaning no direction.
And now if it
And now the
so
external force is giving it a direction.
so hasn't it changed direction?
So when you take a human being and a car, we confuse ourselves a bit. What about a stone?
No, Ben, answer. If you have 0 cities, if you have 0 cities and now you have say 5 cities, haven't you changed from 0 to 5?
Yes.
So if you have no direction and now external force has caused you to change direction or move to another direction because you said you have no direction.
No, I have no direction. So how can you cause me to change the direction?
Ben, let's look at the
So what
reference
is change?
frame.
Yeah, let's continue. Please, let's continue. Let's
What
continue.
is the meaning of change?
But this one, we did reference frame. We did the reference frame.
Hello,
reference
sir.
frame.
Yes.
Direction is at the point of reference. Someone's east can be someone's west. So you can say that there's no direction. The stone where you are standing, where you see the stone, where you are facing is the stone direction. Where another person is standing and facing the stone is the stone direction for that person. So you can say that the stone has no direction. It has direction.
I hear. Let's continue.
That's true.
Yeah, Clement. Yes. So let's talk one after the other. Clement, your hand was up.
My hand was up before Clement.
Come again.
My hand was up before Clement.
Okay. Because I just.
When we go for assembly, in the morning we tell the students about 10, left 10, right 10. The children are facing you, but you tell them about 10, they will turn to their back. You tell them left 10, they will turn. So it's possible someone will be stationary and you still have you can change direction. It doesn't necessarily mean
simple.
Simple. You move him before you change. No.
It's as simple as that.
Maybe sir, I asked this app, can a stationary body change direction by an external force? That's a good question. Stationary body can start moving when an external force acts on it, but it cannot change direction unless it is already in motion. Why? When the body is stationary, it has no direction of motion.
Let's continue. Let's continue. Let's continue. Why? Let's continue, please.
Hello.
Maybe say because from secondary school and one and I what you say?
Hello.
We win
again.
Hello, sir.
It seems like you people are not trying to understand me. When a body is at motion, what is the total force of that body? And when the body is at rest, what is the total force of the body?
Zero.
So zero. So when you are standing and you are facing north, are you having direction or not?
You have a direction.
So if you are standing and they say, where are you facing? What will you say?
The north.
So it's not a direction.
It's a direction.
If somebody pushes you and you turn your face, now the force that is now acting on you to change your direction. So at that point, it means that there is a motion in you before you can rotate. Because once you are not having a force, you can't move. There's no acceleration. But
yes,
if they subject a force, there is an acceleration. So I'm not saying that the body that is standing will not move before it changes the direction. That's not what I'm saying. I think you people are getting me. When you quoted that statement, I'm not saying that a body can just stand without no force and it changes direction. That's not what I'm saying. I'm saying that when the force acted on the body which is standing can change the direction of the body. That is what I'm saying. Okay. Do you get me right?
And has it been rotation?
Yes. So you can't say that when it's only change the direction of the body for moving object. No, it's not only moving object that it can change the direction. It can change the direction of a body that is at rest once there is a force subjected to that body. So that's the definition we said. We said what? Newton's first law states that a body continues to be at rest, or if it's moving, continue to move with what? A constant speed, unless it is being acted upon by an external force to either change the velocity, that is the speed, or the direction. So when you are standing and then they push you, are you not changing your speed?
Yes, you are.
You're changing your speed. So the same way, once you change your speed, your velocity can be changed. Your direction can also be changed. So that is what I'm saying. I'm not saying that you cannot just move and then you change direction. Then what force will cause you? What force will cause you to move?
Yeah, that's impossible.
So that is the definition, please.
Okay.
So it's good for us to disagree and then agree on. So we are saying that the first law stated that. So it states that in the absence of a net external force, a particle moves with constant velocity. So that is anything and everything learn to keep doing what it is doing, which
Sephestus.
Yeah.
Can you say that a particle at rest is a form of state of motion?
A particle at rest? No.
It's not in a form. It's not in a state of motion.
No.
Okay.
You see, a body can move with a constant speed, but that body will be in motion. Okay. So when you are moving and you are not changing your acceleration, it means that you are in constant motion. But if you are at rest, you are not in a state of motion.
Okay. Okay.
That is anything and everything learn to keep doing what it is doing in its inertial frame or in its frame. Frame.
A B, mute your mic, mute your mic.
Okay, so the first law is therefore the law of inertia. So you can also say that the first law is therefore the law of inertia. And inertia simply means mass. So we can say inertia is the same thing as mass. So the reluctant movement of the body we talked about. So we talk about is that, so the heavier the mass, the resistance it is to move. Because if you apply a force to an object that is, small in size, in other words, that is that is not heavy, and then you apply that same force to a heavier object, you will see the difference. And so that's why we're saying that the inability of the body to move is the same thing as, or it depends on the mass, or it's the same thing as the mass of the body.
Yeah.
Hello.
Wait, I want to ask a question.
Hello, sir.
Is there a difference between?
Yes,
please, under the Newton's first law,
yes,
from that is anything and everything that was learn or use. That is anything and everything we use to keep the learn to keep. Oh, okay. Thank you.
So I want to ask a question.
All right.
The inertia, you have inertia without and inertia with the are they two different things or they are the same?
The inertia with
at the end, and inertia without L, are they the same or they are the same?
Inertia. There's no L.
What you're talking about is initial. The L one is initial. Okay. It's not inertia. It's initial.
There's inertia without L. And then in the slides, as we started from the beginning, I'm seeing non-inertial reference frame and inertial. And there's an inertia without.
It's inertia. If I'm writing
No. What you're saying is inertial frames, not inertia.
This is
so
inertia
it's in a
frame.
It's in a sentence.
This is inertia. This one. This is inertia. It's not without L here. It's without L here. Mass is inertia. Ibrahim, are you getting it? Or who has the question?
I think
it's not the same as the inertial, right?
No, it's not the same thing.
Okay, thank you.
I think inertia is like the adjective or something of that sort. Inertia is the noun itself.
It's a noun. It's a noun.
Yes. The noun itself. Sir Festus.
Yes.
I've seen some definitions in the slide, and I want to see whether it can be used for literature or for like examination. That is the first law. It says that in the absence of forces, a particle has zero acceleration. Can we use that as the Newton's first law of motion?
That's perfect.
Okay.
That's perfect. So what is trying to say is that whether you are moving or you are standing, once there is no external force acting on it, you are not accelerating. So that's why I said a body can be moving with a constant speed. So let's say you drive the same speed from one point to another. You've not accelerated. So if you find your acceleration is going to be zero because it's going to be the final velocity or speed minus the initial. So once the speed is constant throughout. So if it is like 5 meters per second that you start with, I'm just using that one, not per hour. Then and you ended with the same thing. So 5 minus 5 is 0. So 0 divided by the time is going to be 0. So your acceleration is 0. So it means that there is no external force acting on it. So it can also be defined that way. In the absence of external forces, the body has 0 acceleration.
Okay, thank you.
Okay, so let's see where we are. So we're down with the frame of reference. Okay. So now we are talking about the mass, where we are saying that the mass is the same thing as the inertia. We know mass. an object. So when we talk about the mass of an object, is the property that specifies how much resistance it is. So that's what we are using as what? The inertia. So here we can write the mass as this. If you are saying that the change in the object's motion, so can be written as change in v. So once you are changing the velocity, means that the particle is going to move, the location is going to be changed. Oh, sorry, let me plug my charger. Okay. So now when you change the velocity with respect to time, then they will give us that will give us the acceleration of the body. So the body is going to have an acceleration. So once there is a change in velocity, so the change in the velocity with respect to change in time, change in time. So this will give us maybe the final velocity minus the initial velocity divided by the final time minus the initial time. And we will now have our acceleration. So we only get the acceleration provided there is what? An external force. And this is the formula for the force from the Newton second law. So if there is no acceleration, it means that no force. And in that case, your object is going to be at rest.
So is it going to be only at rest, or if it is moving to maintain its constant velocity?
Yeah, depending on the status of the body. So whether it is moving or it has rest. So if it's at rest, it means that the net force is zero. If it's also moving, it's also have a zero net force. It moves, but the acceleration is zero. So that's why I was saying that if you are moving with the same velocity, so the final minus the initial is the same. Final is the same thing as the initial. So when you take the difference, you get zero. But that doesn't mean that the particle is not in motion. It is moving, but just that it has not accelerated.
Okay, thank you.
Okay. So,
Festus, if I might come in, please, colleagues, if you are done with the question, then you kindly lower your hand, or else it might confuse the teacher when he wants to call this. Thank you.
Thank you so much. Okay, so velocity is constant. It's constant where there is no resultant force. Resultant force. Okay, so when you are moving with a constant velocity, it means that your resultant force is zero. Or when the vector sum, of the forces is zero. So the first law can therefore restate it. Stated that in the absence of external forces, or force, no, let me put it force, external force, a particle has zero acceleration. Okay. So can we move on? We are clear with the first one. All right. So now the second one.
No, sir, please, I think we are entitled to about 10 minutes break or 15 minutes. Colleague, what do you think?
Sundays, there no break.
Well, maybe somebody will have to go and do some
but you can go for break. Yeah, you can go for back. Sundays, there no break. That's why we close at 11 instead of 11:50.
Oh, the class is supposed to be at 11. It is 4 hours class. It's a 4 hours
class.
class. Yes, so from
7 to 11 is 4 hours.
11. Yes, so it is within it that you go for that 10-minute break.
So if it's time that you want to go, let me know.
Same patch.
I think we should go for 10 minutes break.
Same patch, Festus. Patcho, old best Sunday and patcho.
If you are not right now, I'll not send it to you. Newton's second law of motion. You are not right.
Sir, we are writing, but just that you have been moving fast more, so there are some gaps in it.
Okay, no problem. I will send it. Yeah, so the second law. Is your time up? The break time up? Is it up?
Yes, it is now. It's supposed to be 9, but now it's 9:07.
We first took our break time before we joined. Well, we started like 7:15 there about, which we were supposed to start at 7.
No problem. No, then we can go on 9:15. Maybe you want to do more washing for tomorrow, but tomorrow is working day. That's why.
You go and use a break to wash. The break time
10 minutes. No, it is maybe 1 dress or 2 dress. That you can't tell. So.
Okay.
Hey, my brother. My brother.
For 10 minutes, I watching. Wow.
Hey, George.
Can't you wash two dress in 10 minutes?
Please, you are using your break time like that too. All right. So, what is Newton's second law of motion? So we end at that and then we'll go for a break. I said, what does it stated? Anybody?
Okay, so the rate of change. The rate of change of momentum is directly proportional to the applied force and take place in the direction in which the force acts.
All right, that's fine. Okay.
So that is,
okay, say it.
The acceleration of an object is directly proportional to the net force and inversely proportional to its mass.
The acceleration is?
The acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass.
Okay.
Is directly proportional to the force applied on it, and inversely proportional to the object mass.
Okay.
Why is it inversely proportional to the object mass?
That you just this thing.
Why you state it that way is wrong.
So it's not the opposite, rather.
How do you define the second law? Newton's second law is this.
So Festus,
You
sorry.
said this thing, the mass of an object, not you said, the mass of the object is the amount of substance in the object that resists the change in direction.
Mm-hmm.
And we know that an object moving has an object, when a force is applied on an object, it has an acceleration.
Mm-hmm.
So if the object resists the change of acceleration, that means that the force, there will not be any, it resists the change in direction, there will not be any acceleration.
Mm-hmm.
And if that the acceleration changes, that means that the amount or the resistance of the object is low, and that's why you say that it's inversely proportional. So if one is able to, if an object is able to accelerate, then that means the resistance is low. But if it's able to resist it, that means that its acceleration is also low.
Well, you have a point, but that is not what I said. I said mass is the same thing as inertia. And I cited an example that the force that you apply to an object that is not heavy, when you apply the same force to a heavier object, you see that the way and manner the non-heavier object will move will be different from the heavier one. So it means that a heavier mass needs a higher force or a stronger force. So the smaller the mass, the smaller the force will be able to accelerate it. So the heavier the mass too means that the stronger the force. So the force is proportional to the mass. That is what I said. So you can't say it's inversely. Look at the equation on the board. The force is directly proportional to what? MA. So
MA.
force, yes, this is Newton's second law.
Yeah, but the second law said the acceleration that is inversely proportional, not the force. Is the acceleration that inversely proportional to the mass?
No.
Like acceleration the subject.
Acceleration is inversely to mass. Okay. I thought you are saying the force is inversely to the. Okay.
No. It's acceleration that's inversely proportional to the mass. We are using acceleration. So acceleration is directly proportional to force, but inversely proportional to mass.
To mass, perfect. If you are saying that, it's fine. I thought you are saying that the force is proportional to acceleration, but the force is inversely proportional to mass. Okay. If the acceleration, that's fine. Yeah. Okay. So that's it. Okay. So it says what the time rate of change of momentum is directly proportional to the applied force. That is the second law, and it can be deduced as this, because mathematically this is what it means. Said F is proportional to what? Change of momentum, and we know that momentum is equal to mv. Then when you have change of velocity, so it means your momentum will be equal to mv minus mu. So what Newton's law says, this one is proportional to m in bracket final minus initial, then and they say well, the rate of change divided by time. So v minus u on time is nothing but what? Acceleration. So this is v minus u over t. So we can say that our force is proportional to ma. And then when we introduce the constant of proportionality, this is equals to ma, but we always take k to be 1. So that's why we always say this is Newton's second law of motion. Okay. So let's try that one and we'll go for a break. Then we'll come back. So it says that the rate of change of momentum is directly proportional to the applied force. And the object moves the direction of the force. Direction of the force. Okay. So which means that F is proportional to M V minus U and T. Okay. So this will be equals to where K is equals to 1. All right, so then let's go for our 10 minutes break and come. We are coming at exactly 9:25, please. Don't go and then wash and forget that we're in class before. All right, so meet 9:25.
Okay.
Catherine.
Yeah.
I've not seen your face before. This is the first time I'm seeing your face.
Is that so?
Oh yeah, let me see your face.
Please, oh, please.
You want us to know that you are eating?
I was muting myself. What did you see? Oh? I was muting myself.
You are a slim macho like that.
Please, oh, please. No one should see my face. Erase my memory.
I'll see your face
erase
now.
my memory from your head.
I didn't know you are a slim macho like that.
Ah.
Yeah. Like that's true. You see, explain the acceleration bit for me. I'm not getting what you said. Though.
The acceleration, no. So
yeah,
you said
that
the acceleration of a particle is directly proportional to the force applied to the particle, and inversely proportional to its mass. Do you get it? So mass is the resistance in change of what direction?
Direction.
Do you get it? And once we also say that force is directly proportional to what? Acceleration. That means that once an object is accelerating, that means the force has been applied. Do you get it? And for the mass, it is resisting the force. So if the mass is able to resist the force, that means the acceleration will be what? Low. That's why it's inversely proportional. So once the mass is high, acceleration will be what? Low. And once there has been an acceleration, that means that the resistance to the changing direction is what? It's minimal. So that means acceleration is high by but mass is what? Low.
But hello, Castle.
Yeah.
Wait. So if acceleration is high, okay. If acceleration is high, then mass will be low, then force also be high.
Yes.
Then if acceleration is low, mass is high, then force is also what? Low.
If acceleration is what?
It's high. Mass is low.
The force can be constant in the sense that you can apply the same force to different masses to yield different acceleration. You get it? So for the force, that's why you say that F is equal to ma. You get it? That's why you say that F is equal to ma. So the force there, it remains constant. You can apply a force to a certain mass. The acceleration will be different from the same force applied to another mass. I hope you get it.
Depending on the mass of the object.
Yes, so it's depending on what? The mass.
The mass of the object.
The force depends on what? The acceleration depends on the mass. But the force there, it is directly proportional. It doesn't depend on the mass or the acceleration.
Okay.
Or should I say depend on both? I'll say it depends on both. Since it's directly proportional to the two of them.
But
yeah.
I also think that in as much as that is valid, first of all, that is not the main law. This is just a deduction from the main law. The main law is just where they say that the time rate of change of momentum of a body is directly proportional. So this is a deduction, and the reason why I am pointing this out to us is that, as physics teachers, we need to understand that this deduction doesn't always hold. It doesn't always hold true, especially when you consider. Come again?
How does it not hold?
Yes, it doesn't hold true, especially in circumstances where, especially the two bodies are falling freely under the influence of gravity. When two bodies are falling under the influence of gravity, acceleration due to gravity is constant for all bodies, because at that point the mass will be inconsequential. And so
if acceleration,
this particular deduction doesn't hold true for bodies that are falling under gravity or bodies that are.
If I may come in, you said that once it is falling, the acceleration is what? Constant, right?
The acceleration due to gravity is constant, irrespective of the mass.
Since it is constant, then it follows the law of motion, the first law of motion, that there's no force applied to it. I hope you get me. If it's falling,
what I'm trying to say is that we are looking at the second law of motion, which states that, okay, let me now quote the deduction that Francis brought about, that the acceleration of a body is directly proportional to the force applied, and then inversely proportional to the mass of the body. And I'm saying that as much as that is valid, it is not the true state of the law in itself. It's just an implication or an interpretation, and it has limitation. The limitation being when the bodies are falling under the influence of gravity, because when bodies are falling, come on.
You continue, but may I chip it in? Is the force is directly proportional to the mass, not acceleration. So
that's what I'm saying, that the acceleration is directly proportional to the force applied and inversely proportional to the mass.
Yeah, so no, if you go
please, if I may come.
F is equal to ma, right? So we are saying that the force is directly proportional to the mass, and not force is directly proportional to the acceleration. That's the only part I want to correct. You can go on.
F is equal to ma, right? So when you make A the subject, you are going to get A equals F on M. So A and F are related directly, and then A and M are,
yes, they are related. But in this context, if you relate the force to the acceleration, you'll be wrong. That is what I'm saying. No, it is. I'm coming. It's only change of subject. I'm coming. It's change of subject that we are talking of here. It's change of subject. Can you remember that when you were doing this same thing, this argument club, when we were doing the 20th physics, and I remember Madame Foriwa explained to us that the force, and that is exactly what the first said. He said that the force is proportional to the mass. If you want to say you are making it a subject, that the F you go and divide the M, you are going to get acceleration is called force over mass. Yes, that is when what you are saying will come in. That it will not hold for certain cases. Do you understand? For instance,
no, but I'm not even emphasizing on the force. Listen, I'm not even
emphasizing on the force. I'm not contradicting what you are saying.
My emphasis is on the fact that we are looking at the.
I'm not contradicting what you are saying. I'm only saying that when you use mathematical deduction, to make A the subject, you may be wrong. That's all I'm saying.
Hello. Can I come in?
Yeah, first, yeah. Go ahead, Castro.
All right. So one thing I heard was under gravity. It's constant for everyone, for all of them, right?
Yes, irrespective of the masses. It doesn't depend on the masses of the body.
Good. It's constant for. So remember in this thing, in Newton's first law of motion, we know that once something is in constant motion, there's no force applied to it, right? Once it's in constant motion, there's no force applied to it.
Yes.
Good. So if there's no force applied to it, then there's no acceleration, right?
So that's a different perspective. Here you are talking about the situation where there is no acceleration. But I'm talking about the situation where there is acceleration.
It's constant. So if the acceleration is constant, we assume that there's no acceleration. Because once it is constant, then that means that there's no change in acceleration.
No, if acceleration is constant, it doesn't mean there is no acceleration. It means that it is not changing.
There's no change in acceleration.
Absolutely.
If there's no change in
acceleration, I'm talking about acceleration, not change in acceleration. And acceleration for the two bodies that are falling freely under gravity. The point is that
moving at constant acceleration, which is gravity's acceleration, right?
Yes, acceleration due to gravity.
Good. So if we say that a mass of body is moving on a hill at a constant velocity of this.
Constant acceleration, not velocity.
A constant acceleration of this. Would it say that there is a change in acceleration or there's an increase in acceleration?
No, there's no change.
Good. So that means that the A is what? 0.
No. A is not 0. A is constant. Constant doesn't mean 0.
Kevin,
what is Newton's first law of motion saying? What is Newton's first law of motion saying?
Can I come in? Hello.
Yeah, come in.
I think that let's go. No, I think we need to go one at a time. When more than one person is speaking, it confuses us. Because yes, the concept of velocity and acceleration. When an object is moving and its speed or velocity changes, that is acceleration.
Yes.
We all know that already. So once an object is falling under gravity, gravity will be causing it to move faster. So there's always acceleration. You understand? So even if it is changing faster at the same rate, there is still acceleration. So acceleration is not 0. Unless the object is not speeding up at all.
Constant acceleration is never 0.
That is it. So even if acceleration is 1, it means there is a change in velocity.
Yes, just that it's constant.
So it is not 0.
Okay. I get where you're coming from now. So all right. So let's say that acceleration due to gravity is made of 1, independent of the mass.
Please, one person, so that we can understand what is going on.
Okay.
Someone is talking in the background. We don't know who it is.
All right. So,
what's the problem?
If I'm getting you right, if let's say gravity is like 1, or let's say 2, irrespective of the masses, the acceleration is always 2, but the masses will make you know which speed it is, which force is being applied on it. Isn't that right?
Yeah. So if gravity is 1, that means there's acceleration. If it is 2, there's acceleration.
Yes. All right. Okay. I get what you're saying.
So the only point I'm trying to make is that deduction that my friend Francis brought up, though is valid, but it is limited. That is why that is not the original law of motion. That the original law is the time rate of change of momentum of a body is directly proportional to the force applied. And the one
takes place in the direction.
The one that my friend brought about is when you make it mathematic, some mathematical logic, and it doesn't always hold because you are comparing mass and acceleration, and you are saying that they are inversely related. But when you are considering freely falling objects, the acceleration is always constant for the two objects, irrespective of their masses. And so here, wouldn't work.
What is the argument?
I said it was about the formula, which is A equals F over M, which is acceleration directly proportional to the force and inversely proportional to the mass of the object. You're saying that it doesn't always hold true for that deduction. It doesn't always hold true for that deduction, but I'm not really getting it because it's the same thing as the first one that was written, which says that in the first law, it says that in the absence of a force, or what was it, the Newton first law, in the absence of force, a particle has zero acceleration. It's the same deduction. And we know that F is equal to ma. So if you're doing the mathematical deduction for it, won't you hold for all instances? If you're doing classical mechanics, that is.
Oh, okay. Yeah, so this is the law. F is equals to mass times acceleration. So that is the Newton's second law.
Yes.
Now, if you make A the subject here, so you are going to have F over M. Now, this one can hold based on certain conditions. So if you are looking at it in the horizontal motion, you can say that if I have the same force, then my acceleration is going to vary. That is, if the masses are changing. So which means that the heavier the mass, the slower the acceleration. So if the mass is also less, then you're going to have a higher acceleration. It means you are considering your force to be constant. You are applying the same force to maybe a small object and then maybe a heavier one. Don't look at the size. You can have something that is very big in size, but it is light in weight, but a heavier one. So if this F and this F is the same thing, so here the deduction will be that this one is going to move with a faster acceleration as compared to this one. So if this is A1 and this is A2, it means that A1 will be greater than A2. So in that case, you are taking the force as a constant force while the masses are changing. But in the case that you are dealing with the vertical motion, so you know that irrespective of the sizes of the mass, once you drop anything, they are all going to fall with the same acceleration. That is the acceleration due to gravity. You get that one right?
Yes, sir.
Yes, so sir. That is what is. This is just a deduction that we can use when you are dealing with maybe horizontal motion. You want to have a constant force. Then you check how does the acceleration varies with mass, or whether when you increase the mass, what is it going to? How does it affect or cause the acceleration? But you can use it based on the mathematical relation, but it based on maybe the area where you are looking at the motion. Okay.
So you mean that with a vertical motion, irrespective of mass, you have the same acceleration, right?
Yes, which is the 9.8 or 10 meter per second. So, but that doesn't mean that the particle doesn't accelerate. It does, but it's constant, because when you are standing on top of maybe a building, maybe you are on the story building, and you hold something in your hand, you see that the particle will have a zero velocity there. But when you drop it, at this point, it starts to increase. So from 0, it moves to 1, 2, in that order. By the time it is getting to the ground state, it will have a higher velocity. So that's why you hear the impact. You hear that there is going to be a contact between the falling object and then the ground. So assuming there is no acceleration, the thing will be going down, then it will just go and land on it normally, gently. You didn't hear anything. But it accelerates, but it means that it goes with what? A constant acceleration. So that doesn't mean that the velocity doesn't change. It changes velocity. Okay.
All right, thank you, sir.
So let's continue from where we ended. So we've written the Newton's second law. So from there, hence we can do this. Oh, okay. Let me take this slide off so I can continue from there. Try to do this. Okay. So hence, you can say that hence for a particle of mass m, the net force on it is always equal to the product of the mass and acceleration. So what we should know is that force is a vector quantity. And it is a sum of all the forces. Okay, so we have to know this. Now, if we have an acceleration, we always say acceleration is equal to change in velocity over change in time. So we can write this one in the form of differential. So A will be equals to dv on dt. So which means that when you differentiate the velocity with respect to time, you will get acceleration. So when you also differentiate displacement 2 times, that's the second derivative of displacement, will also give you acceleration. So we'll be seeing something like this. So A is the same thing as V dot, then which is the same thing as R dot dot. So when we see a letter with a dot, tells us that it is the first derivative of that number with respect to time, or that is that variable with respect to time. So this is a displacement. So the second derivative, that's why it has 2 dots on it. Then the first derivative of velocity with respect to time. So the same way we can write momentum as we know. Momentum is equals to momentum. So as we know, P is equals to mv. So if I differentiate momentum with respect to time, I will get force. So the time differential of momentum will be equals to, now my mass is not varying, so I'll treat it as a constant. So m, then I'll differentiate velocity with respect to time, and this gives me my ma, because this is a from here. So that will going to be a. So it means when you differentiate momentum, the result you will get will be force. So you can write it this way: the P dot is the same thing as F, which is equals to ma. So this one is taking a scalar dot product. Okay. So let's also try to see if we can, from here, this equation that we have, we multiply through by V here. So we have M dV dt is equals to FA from the V. So this one is equals to M dV dt. So if we multiply through by V, so multiply this by V, so this equation by V. Through by V. Then we have F V equals to M. Then we have dV. Let me bring the V first. So MV dV. So that's MV. Then we have dV on dt. Okay. So I can now take the, since V is time dependent, so I can write it like this. This V will now be equals to M, then I'll have D on T, and I'm going to have V multiplied by V. So there is V here, and then there's another V here. Okay, so V times V is nothing but V squared. This is V squared. So V squared, so M d dt on V squared. So we now differentiate this. When we differentiate this, we'll have kinetic energy to have this, to be the same thing as this. So the differential kinetic energy will give us this. That's when you have this term. And I'll show you how you can differentiate the kinetic energy to arrive at this. So what is at the right-hand side is nothing but the differential of kinetic energy. You understand? Because kinetic energy is what? Half mv squared. What I'm trying to say is that this m dv square on dt is nothing but kinetic energy. Okay, because if my kinetic energy is half mv squared, so half mv squared, when I differentiate this one, I'll get 2 m divided by half. So the 2 will cancel the 2, and it will be left with whatever that is there. So let's take it from here. So if I say Ke is equals to half mv squared, I want to show that the differential of this Ke with respect to time is the same thing as Fv. Okay, that's what I want to show here. So we first of all define our kinetic energy, that this is equals to half mv squared. Then we introduce the time differential on both sides. So the T on the kinetic energy be equals to my half is a constant, mass is a constant. Then I will differentiate this one, v squared. V squared like this. Okay, so you can split the V into V dot. So this on that can also be written as this M, then I have D on the T in bracket V dot V. So you apply your product rule of differentiation. So when you have two things that are multiplied, you use a product rule. So this one will be the same thing as half M, then you keep one, and then you differentiate one. So you have to treat one as constant. So V, then I'll differentiate V respect to time. So let's say if I'm taking the first one, so plus, then I also keep the second one and differentiate this one. So this will also be half mv, then I'll differentiate this V respect to time. So now the left-hand side is a differential of the kinetic energy respect to time. Now I'll have half m and then v. Then what is dv on dt is a, that's acceleration, plus half, then mv, this one to also give me acceleration. Now half plus half is going to be 1. So which means that the time differential of the kinetic energy will be equals to half plus half is 1. So that is going to be m. Then I'll write the a before the v. So ma then multiply by v. But I know that my ma is the same thing as what? F. So it means the d dt on the kinetic energy is nothing but the force times the velocity. So this expression is telling us how work is done on the object by the force. Okay. So the left-hand side of the equation represents this. Represents the rate at which the force does work. Ibrahim, are you there? Or you are still watching? The rate at which the force...
Yes, please, I'm there.
Okay. The force does work on the object. That is the rate at which the force transfer energy to the object. Okay, so that is the meaning of the equation. So now we want to now write the Newton's second law in terms of, now we've seen the differential form of it, but how can we write it in terms of what? Integration. So, you know, differentiation and then integration are inversely proportional. So if you have a displacement, you can divide it by time to get velocity. Then you can further divide the velocity by time to get acceleration. Then what about if you have acceleration and you want to arrive at displacement? So you need to integrate. So you integrate acceleration to get velocity. Then when you integrate velocity to, you get displacement. So that's right, Newton's second law in differential form. Okay. So let So let R as a function of t be the position vector of a particle. So for a particle of mass m subjected to a force F naught, along the x-axis. The x-axis, we can say that so from the deduction that we got here, that where is that? I think I've written it here. Where I've written the dot. Yeah, here. So when you have the position vector and you want to reduce it to the force, so you see that the second derivative of the position vector or the displacement vector will give us our acceleration. So we can write our force from this, that the position vector, now we are dealing with the x-axis. So the second derivative of the displacement is the same thing as the force, which is F naught, divided by the mass. Okay. Now, this is the second order. This expression here that we are seeing is what we call second order differential equation. So this is second order differential equation. So we call it ODE, second order differential equation. Now for x as a function of t. So when we integrate this, now we're now going to integrate this. For x as a function of t, so integrating gives the velocity as this. So integrating it gives the velocity as. So we write our x dot dot. So let me write it this way so that we see it clear instead of the dot dot. We know that the dot dot is the second differential. So we have d square x as a function of t respect to dt squared. And that is giving us our F naught on m. So we can write it this way. Can write it d dt, then d dt on x as a function of t to be equals to F naught on m. So I can use first this one. I will first of all operate on the inner integral or differential. So I'll multiply this one with this side. So I'm going to have d on dt, then d as a function of x, which is a function of t, now will now be equals to f naught on m dt. So you are integrating both sides. That is using the definite integral. So what this means is that I can push this one out inside. So here, okay. So I will still have my d of whatever I will get. Then so this will cancel this. So I'm going to have d dt as a function of x of t. You can just write the x if you want. And this now gives us the integral of f naught on m dt. So when you integrate dt, you get t. So we'll have d x on dt will be f naught over m t. Now this is the velocity, because the x on dt is what? Velocity. So it means x dot of t, x dot of t is nothing but, so bring the constant t plus. So the different my t and then the plus. So this is a constant of integration. So this will now be f naught on nt then plus your c. So when you integrate the force, that's the acceleration, you get x as a function of t to be equals to that. So, or you can still write it v as a function of t, but velocity is time dependent, so and so the v as a function of t is equals to f naught times t over m plus c. So that is, so it means when you integrate acceleration, it brings you to velocity. Then you can go ahead to increase, to integrate this one further to get the displacement. So, but since we are dealing with velocity, so our constant, we can just make it v naught, so that will determine as our initial velocity. So you can just put this one as v naught, so that our symbol will be uniform. So we know that the constant of integration is what? V naught. So where v naught is the constant of what? Integration. Okay. So if we integrate the velocity further, so integrating the velocity further, gives the displacement. Use the particle's displacement. All right, so now we have the x as a function of t to be equals to integral of x of t x dot of t. So means that this x of t can be written as d on dt of x as a function of t. Now we substitute whatever we have here. What is our x dot of t here? So that one was expressed as F naught T plus M plus V naught. Now we cross multiply by T. So my dx of T will now be equals to F naught T on M plus V naught, all multiplied by dt. Okay, so we integrate both sides as usual. So integrating both sides gives this. So when we do that, we have our x of t to be equals to F naught. Then when you integrate t, you get t squared. So F naught t squared. Then you divide by the index, so over 2m. So over 2m, then plus, when you integrate this one, so that will be t. So this will be v naught t. Then again, you have to add your constant of what? Integration. So that will be x naught. So we are looking for x. So the constant should be in line with x. So which means that our x will be, can rewrite this, x naught plus v naught of t, then plus F naught t squared for m. So that is from moving from as a force toward displacement, acceleration to displacement. So if you are given a question in terms of acceleration, and then they ask you to find the particle's displacement or position, then you have to integrate. So you integrate the acceleration to get the velocity, then you further integrate the velocity to arrive at the displacement. So this is how we write the Newton's second law in a differential format. So these two laws refers to the response of a single object to apply force. Okay. So how an object is respond to a force applied to it. Okay, so let's look at the last law, which is the third law. So Newton's third law. What do you know about the third law?
He said actions and reactions are equal but opposite.
Your line was breaking, please. Come again.
So Festus, please, he says that actions and reactions are equal but opposite.
Okay, that's fine. So when you say something that is good, the implication will be, or the response will be a smile. When you say something that is nasty to someone too, the response will be a frown face. So that is what the law is saying. It applies in every aspect in life. So in every action, there is equal and then opposite reaction. It says that in every action, there is equal and opposite reaction. So let's take for a system of n mutually interacting point masses. So the ith object of mass. So there are so numbers of number of masses maybe in a system. So we want to pick one of them. So we are labeled that one as the ith one. The I can be the 10th, the 9th. So the ith object of mass or object mass. Object mass mi located at a vector displacement r. Displacement r will exert a force F ij on the jth object. And the object j also do the same thing. The object j also exert a force Fji on the ith object. Okay, so from the third law, what this statement means is that, so from Newton's third law, so Fij will be equals to minus Fji. So the force will be same in magnitude, but opposite in direction. So when you push something, you end up exerting a force on that thing, and then the thing also exerts a force on in the opposite direction. So that is the meaning of in every action there is equal and then opposite reaction. So if you now apply this to the Newton's second law, so applying Newton's second law, we have this. Newton's second law. So we have our force, which is equals to ma. Then we have our m, the square r on the t to be equals to f. Now, so we have so many interacting objects. So we can write what the third law is saying. So when we pick the mi, so that's the ith object with mass mi, then the square r on the t squared will be equals to the sum of all the forces. So j will be equals to I to n, and this will be I plus j. Then we have f ij. So let's say we have particle like these are the particles within the system. Okay. So if you pick one particle like this, so since they are interacting, so this particle will exert a force on this, on all the particles inside. There will be a force from the one that you've chosen to all the particles. So that is the meaning here. So it means that if you want to get the total force on this object here, it's going to be the sum of all the forces that it exerted on the remaining particles within the system. So that's why we are summing it from Fi to N. So N is the total number of the particles present. So if there are 20 particles, then you are taking one out. So you have about 19 forces. You have to sum 19 forces together to be able to now tell the total force that the object one will be exerting or experiencing. So the equation that I've written there is a total, let me give a name, equation, let me say, okay, let me put this one as 1, equation 2. So equation 2 is the total this is the total force expressed or experience. So expressed by I due to all the other particles. Except itself. As an object cannot exert a force on it. Okay. Or itself, and to itself, and itself. Okay. So it means that a particle cannot exert a force on itself. So you can't have any opposite force within your vicinity if there is no other particle around you. Is that clear, please?
Yes, same.
Okay. So you write it like this. So if you are taking the summation of the I1, so it's going to be the sum of the I taken from 1 to N. Then J is not the same thing as I, or I is not equals to J. They have MI the square R on the T square. And that will give us, or that can also be written as I is equals to I N. In the same way, J should not be equals to I. They have F I J. So that is how you express it. So you can get a question, explain why a force cannot or a particle cannot exert a force on its own or itself. That's the reason why a particle cannot exert a force on itself. So this equation, for the right-hand side of this equation, the right-hand side of equation 3, each element of the sum Fij is equals to minus Fji, and therefore they cancel out. So what we are saying is that if you are saying that Fij is the same thing as Fji, and you want to sum them, so you can write it this way: Fij, then we take this one to the other side of the equal sign, you have Fji. But from the Newton third law, we are saying that Fij is the same thing as Fji, unless that they are in opposite direction. So when you take this one to the side, you have this one positive, you have 0 here. So when you sum all of them together, you get 0. So that is the meaning. So from here, I can't make any of them the subject and substitute it here. So if I want to eliminate Fij, so it means my Fij is negative Fji. So this one will be negative Fji. So negative Fji plus positive Fji will give me 0. So that is the meaning of the sum. So when you do it that way, what I'm trying to say is that when I make it that way, it means I'm going to have Fji plus Fji. So you see that you are dealing with the jth particle. Then you have another jth particle. It means you are indirectly trying to find out whether the particle can exert a force on itself. So Fji is itself, and then another Fji. So once they sum up to be 0, it tells us that this particle cannot exert a force on its own. So that is why we are getting the sum to be 0 here, if you take the particle to be the center. But you only get a force or a value when they are different particles. So when there are 2, we'll go with this expression. They are more than 2, then you sum them using the summation. You sum their forces. So what I've stated, that is all the forces that cancel out. So let me write this one. That is the sum of all the forces due to the presence of all particles 0. All the forces due to the presence of all particles 0. So, which means that m the square on the t square of RCM is equals to 0. The RCM is so called center of mass. So where m is equals to the sum of I is equals to 1 to n, then we have mi is the total mass. Then where RCM is the vector displacement. Vector displacement of the center of mass. The center of mass of the system. Which is an imaginary point. Which is an imaginary point and whose coordinate are the mass created averages. Of the system. Okay, so we can define the RCM, which we are calling the center of mass as this. So the RCM is defined as the sum from I is equals to 1 to n. Then we have MIR I, then divided by all these things divided by the summation of the total mass. Total mass, which is mi. And this is taken to n. So that is the expression for the center of mass. So when you take the masses multiplied by their centers, then divided by the total masses to give us the total center of mass. Check something here, model. Okay, so yeah.
So that one is I is equal to I.
1. It's I is equal to 1, all of them.
One. Okay.
So let's leave this one as 4. So once we can write it in terms of displacement, we can extend it to momentum. So we also want to find the momentum of a particle due to several particles that are interacting. You also write it in the same way. So the momentum will be the differential of this, the vector displacement. So in terms of momentum, it's going to be P equals the summation of I is equals to 1 to N. Then we have mass, then the MI, so the differential of R respect to T, so I. So that you differentiate this, you get V. This will be the sum of the momentum. So if you are looking at PI, the momentum of the I object, so you have this. All right, so looking at something in the model. Okay, after this, I come to Unit 2 model projectors. All right, so let me check in this before we can talk about that one. Okay, so the total momentum is also going to be written as that. So this is a conserved quantity. Let me write on it. This is a conserved quantity irrespective of the force acting. Of the force acting between.
Yeah. Festus.
Yes.
Good morning.
Good morning.
Yeah, how are you going?
Yeah, normal.
Everything looks normal. Are they all online? I've seen 18 people. Okay. Good morning, class.
Good morning, dog.
Morning.
Good morning. Yeah, I hope you are all doing well.
By the grace.
Yeah, we thank God. We thank God. I'm also doing great. Classical mechanics is very interesting.
Very, very interesting.
It's very interesting. So, when you understand classical mechanics, you understand life. So get all the everything. All right. Even though it's more mathematical, but it's very interesting. Okay.
Yes, dog.
Don't manage. Get it, and then apply it in your life.
Oh, we are managing.
Especially when you get to the dam oscillations and all those places. All right, Festus.
Sir.
Yeah, I'll leave you to continue. Okay.
All right.
Okay. So you guys, see you.
Okay, no. See you. See you.
Bye.
Okay, so this is a conserved quantity irrespective of the force acting between the various system, between various of the system. So what we are saying here is the principle of conservation of momentum. And when you talk about the principle of conservation of momentum, so principle what it says is that if the net force acting on the particle is zero, then its momentum will remain unchanged. So if the net force its momentum means unchanged. So whether we saw this, the differential of the momentum is force. Okay, so the moment this is 0 means that there's no change in momentum. If the force is 0, the change of momentum is also 0. So it means there's no change. So let's just look at Newton's third law and then conservation of momentum. Okay. So if you consider an object, considering two objects, one and two. I write it in the way so that we first. 1 and then 2. Let the force that exert. So let the force exerted by body 1 by the first body. So by body 1 on 2. Body 1 on body 2. The F12. F12 and the force of body 2 on 1 be F21. Okay, so we can have this if we have the system which comprises of 2 bodies. So this is 1 and this is 2. Now the force of 1 is exerting on 2, and then 2 is also exerting a force on 1. Then there is an other force which is, let's say, F external. Then F1 external, let's say F2 external, and this one will be F1 external. So the external forces, consider like there are other forces around. So the sum of the other forces is what we are taking it as the external. So if we have this, now from the Newton's third law, so we are saying that the magnitude of F12 should be the same thing as the magnitude of F21. So the values of the forces should be the same thing. The only thing that is different is the direction of action. So you can see it here. So this will be F12, and then this is F21. So you see F12 is acting to your right, and then F21 is acting to the left. But we are presuming that the magnitude of the force is constant or same for the two. So this implies that from here, the Newton's third law means that we can say F12 is equals to F minus F21, sorry. Minus F21. But this is what Newton's third law is saying. Okay. So, and we let the external, let F external, F1 external be the forces expressed, be the force expressed by object 1 as a result of the presence of other forces. Of the other objects. Then the same way, also let F2 external also be the force expressed by object 2 in the presence of other, as a result of other, or in the presence of other object. Other objects. Okay. Now we will now write the total force Okay, so the total force that you will get force or net force expressed by object 1 and 2. One and 2. So you first of all pick the object 1. So the sum or the total force by object 1 will give us the force due to the second one plus the force due to the other particles or objects. So what was my last equation? 5. So no, I didn't want to say, okay, 5. So this is equation 6. So equation 6. Then also get for F2. F2 will be equals to F21 plus F2 external. So equation number 7. So from Newton's second law of motion, the rate of change of momentum is proportional to the applied force. So you write that, so from the second law, Newton's second law, momentum is proportional to the applied force. So F is proportional to M P minus U on T. Okay. And we also know that the differential of momentum is force. So our total momentum, which will be our total force, we saw this one earlier on, is going to be the sum of the two forces, that is F1 plus F2. So it means momentum differential is equals to what? F1 plus F2. So we sum them together. So if you want to, you can write the momentum in terms of 1 and 2. So when you want, you can also sum the momentum together. Okay. You can also write this one as P1, the F1, which is this, and P2 is that. So if we now sum everything together, our P dot will now be equal to our F1 is F12 plus F1 external, then plus F21 plus F2 external. What we are doing is that we are proving this because of the statement we made here. What is that statement here? Yeah, this statement. It says that if the net force acting on a particle is 0, its momentum, so its momentum remains what? Unchanged. So this is what we are looking at. Okay. So now that we sum all of them together, we will now make this one the subject, the F12 the subject, and the substitute by using the Newton's third law. But from the Newton's third law, F12 is the same thing as minus F21. So in place of F12, we put minus F21. So our momentum dot will be equals to F12 now become negative F21 plus F1 external. Just erase it. Plus F1 external so F1 external, then plus F21, then plus F2 external. So F21 cancel F21. So our P dot will now be equals to F1 external plus F2 external. So they are all external forces. we can let F1 external plus F2 external to give us an external force. But that's all external. So when you sum them together, you still get external. So we'll have that. So it means our P dot will now be equals to F external. Now, the external is the net forces that are acting on the system. So if the net force is now 0, so where F net, so say where F external is the total external force, external forces acting on the system. Acting on the system. So in the case that this becomes 0, so in a case where there is no external forces, when F naught is 0, is 0. So we presume that the system, there is no external forces acting or influencing the system. So we'll have our P dot to be equals to F external to be 0. So which means that our P will be 0. So when there is no external forces acting on the system, we'll have our momentum to be constant. So once you get a 0, 0 is a number, it's a numerical value, and it's a constant value. Okay. So that's the meaning of the statement that says that once the external force acting on the system equals to 0, it means that there is no change in momentum of the particle or of the system. So you can conclude by saying that hence, in the absence of external forces or external force, the total momentum of a system is constant. This is the principle of conservation of momentum. All right. Yes, are we there?
Yes, sir, we are here. Some of us just came, so we are not.
So we are listening.
We are just listening.
So we are here. We are here. We are following.
So we are following. We are here.
So that is that when you have so many particles that are interacting within a system, so once you presume that there shouldn't be an external force, it means that there's not going to be a change in momentum within that system. You know, the force and then the momentum are interrelated by differentiation. So when you differentiate momentum, you're going to get a force. So once there is no external force, momentum 2 becomes 0. Okay, so let's look at dynamics of a system of particles. Particle dynamics. Things change. Okay. So a system of particle means a group of particles interrelated to each other. So that is the meaning of system of particle. This could be discrete when considered as separated and continuous when they are not. So within the system, you can have particles that are individualistic, and then in the case when they are together, so you'll be looking at a constant, a continuous particles. So discrete. However, so when you have a system that has a large number of discrete particles, in the point of classical point of view, you see that the particles are behaving like they are continuous particles instead of being discrete. So let's say you have a lot of bees put in a basket, then when you look at it, they look like they are together because of the number. So it means that we can say continuous system can also be considered as a discrete system, or no, a discrete system can also be considered as what, a continuous system. Okay, so let's look at center of mass. Center of mass. I have 5 minutes. I want to introduce this new concept. Okay, so we'll end at this. So when we meet next week, we'll continue from center of mass. So let's see, any question from where we started up to this point? Yeah.
So this one is more like a question. I just wanted to find out something.
Okay.
On the timetable, when we are about to start, this week was supposed to be face to face. That means we are all supposed to go to our centers for the lectures.
Please, I would like to come in here. Please, it is not face to face, okay? The academic calendar said online or face to face session, okay? It's either online or face to face session. And from their the time schedule that came out, this second block is not face to face. There's no face to face. All is online for all centers. Okay. Normally, if it's face to face, it will be for 4 centers that will having a face to face, and the rest will be online. But this time, everybody is doing online, so there's no face to face. Okay, so please don't mistake because of the academic calendar saying that online or face to face. So we're supposed to have face to face. No, that's not it. We are having online. Okay, thank you.
All right. I hope you answered.
Okay, I'm okay. Thank you.
Yeah, any other thing?
Welcome.
Any other question? Okay, then in the absence of further questions, then we'll pause here and then continue about with the next week. Because we are left with just some few minutes, but this is a new concept that I wanted to introduce. So let's start in our next meeting.
Yes, sir.
Sir, please, a reminder of the note too, please.
No, I've heard you.
Okay. Colleagues, please. Hello.
Oh, you can talk. You are listening.
Yes, please. Those of us in the physics personal group, I'm going to put a link there. Please. We want to set up a group. So you can click the link and then you see what the group is about. If you are interested, then you can stay on. If not, you can leave. So the link will be in the personal group.
But what time are we meeting this evening?
Pardon?
Hello, we are going to meet this evening for quantum mechanics. I want to know what the time you are meeting.
We are not meeting for quantum mechanics.
We are not meeting.
I will have
I'll
have to call this thing. Say about it.
Oh, okay.
I have to call him. Say, do you have his number? I don't want to have
his number. I have his number. Are you supposed to meet him this evening?
Yes, you're supposed to meet him this evening.
What time?
We discussed that.
Castro, I don't know what
yes.
Man. Sir, it was only the can say electromagnetic, and the rich consensus say, Senyamipa, yeah, agree say, 2 hours, maybe 2 hours. I want normal days now. Not 2 hours now. And they have a Sundays, 12 to what do you call 12 to 2. And I just like a kind.
But I never be. Sunday Sunday, really.
Now say and you man I am one.
So 4 to 6 a.m.
4 now be 2 to 12 to 2 is not a number.
No. For today, listen, for today I couldn't call him, so today we can't do the 2 to this thing now. We can't do it that time. Okay? Because it's not aware. So he has to now prepare. So for today, we will do it the evening time, which should be around 4 to 6. If that's okay with members, or else today we won't be able to do anything. Unless maybe we start with next week. So what do you suggest? Members, what do you suggest?
Next week is yes, yeah. Or I tell you to see where for 2 hours now. The Sunday for 2 hours.
But please, I want
hello,
that it will be a meeting. So why don't you make this even?
Members, I'm listening. What is your
Madam,
suggestion?
near you. Electromagnetic.
Please, one person at a time. It seems everybody is one person at a time. It seems everybody is on floor.
Hello, please. Let's make it one person at a time. Okay, please, I'm begging you. Let's make it orderly. So the question on board is that we told him that we would like to meet him and divide it into 2. All right. And we were supposed to discuss and get back to him. We discussed it, but there's only a few members that were present at the discussion after we were done. So now, what the few members put across was that we will make it Sundays and the Wednesdays. So 2 hours each. On the Wednesdays, it was ascertained that we will start at 6 and end at 8. So for the Wednesdays, that is done. But the additional time, which is the Sunday, those there mentioned that we should start at 12 and end at 2.
Yeah.
Okay? Now, we have almost all the class here. So what, and the thing is that for today, we can't make it the 12 to 2 because he isn't aware of the day and time we discussed about. Unfortunately, I was supposed to do that. I couldn't do that. So today, if you're supposed to do today, we can only do it in the evening. Okay? So the first thing is that today, you will do it or make it next week Sunday, rather. Should we start the Sundays today or should we start next week Sunday? That is the first one on board. I need your suggestions.
That's true. Can I talk?
Yes, please.
We can do it today. Since he was aware we are supposed to meet him today.
Exactly.
Yeah, so we can start today, but the time, like you said, 4 to 6 is okay. For me, I think 4 to 6 is okay.
All right. So anyone with a different opinion apart from today meeting him, do you all concord that we should meet him today?
Yes, I agree that we should meet him today.
Me too, I agree.
Anyone else with a different opinion, please, if you have a different opinion, let us know. Benjamin, I can see your hand up. Benjamin, I can see your hand up.
Is it Bernard or Benjamin?
No, Benjamin Pierre's hand is up. Bernard, you can also talk. I see your hand.
Okay. I agree with what my colleagues are saying. Let's meet this evening. But if he is not ready, let us know before time.
Okay.
Yeah. Thank you.
All right. So I think for today, we have agreed that we can start the meeting today. So now what is left? The second one is the time. The time, what I suggest today, what was suggested today is 4 to 6. Anyone with a different time apart from 4 to 6, for the 12 to 2, it can come on. So right now we are contemplating evening time. So evening time, which time should we start and which time should we end?
All right, Kasho.
Mm-hmm.
So, well, I think here we have
actually arranged on 4 to 6. But then I think it will also more rely on the man himself. Probably whatever discussion we have here in terms of time may not even suit him. So I'm suggesting you get back to him first. Then when the time that will be convenient to him, you communicate that to us.
Let me call him right away and see.
So the issue is that if we do get the time, then we can know the time. I can know the time that he can make it. So let's say if it is kind of like 4 to 6, okay?
I think 4 to 6 is okay, but then he should confirm it.
Okay.
Yeah.
So Felicia, I think she's calling. I think he's calling him. And my
Hello,
brother,
Castro.
I'm listening.
Okay, I think that if you have agreed on the time, it's fine. It's okay, but maybe what I said, I shouldn't have mentioned it here when we have this class. But we need to also to encourage him to write. Well, I hope that this time we all come at a unified voice and tell him that he should do more of writing, because that is why maybe I shouldn't have mentioned it here in the presence of the Festus. That one was not right. But when we start, let's let him write. We should have the Festus write a lot, and then it helps. Sometimes we ask for the note. At our spare time, we match it, we compare his note to the one that right. It helps a lot. But this issue of highlighting and pointing to it would not help, especially when this electromagnetic is all about proving. So I beg, if you can talk to him on our behalf, fine. If not, when he comes, let's insist that he writes. This highlighting doesn't help some of us at all. You can remember when we were doing Tema, I talked severally. He said, "Oh, he's writing part. Now we started a new course. The writing part is still not ready." So I beg. Everybody, you see that people learn by observing, others learn by writing. Me, I have to write. Thank you.
All right. Okay.
Hello, colleagues. Hello, colleagues.
Yes.
I called him right away. So he said he was waiting for us to call him yesterday. So I told him that we were not certain with the time. So we just concluded that we want to meet him at 4 to 6. He said it's okay.
All right. So I'll call him again and let him be aware. The 4 to 6 will be for only today. The rest will be for, and I think I should also put it across again since majority are here. Do you think that a Sunday slot to 2 is okay for each and every member or majority of the members? Bernard, I can see your hand.
Okay, me, I have a problem with it to Castro because our lesson will end at our online lectures will end at 11. So I think the two would do so that we have some minutes of rest. If you have something doing, you do it quickly, and then you come back. But ending the lesson, and then you have barely an hour for the next lesson. I think that should have been on Saturday, and it's a little bit of stress. So that's my opinion, though.
Okay, so please, I will want us to, if you have a different opinion, you state it, and then you state your time that you think it will be convenient. For now, what is on the table is 12 to 2. So if you have a different opinion, then you state the solution to it. Then you vote on that. Okay. All right. So I can see.
Okay.
Bernard. Yeah, Bernard.
Yeah, I think that once he has decided, I think that we should let him choose. If he's okay, then we just go. That's what I think, anyway.
Well, we are the ones seeking it, so we should set our time so that he will work around us, and that's why he told us. Okay. So for us, what we need is that we set our time, then he will work around it for us. So that's why we need a time for it. All right. So Francis, I can see Francis, your hand is up.
Yeah, thank you. The rest is very important. Because you can't sit in for 4 hours from morning to 11. The right away, we are starting at 12 o'clock. I don't think it's
So,
working.
Francis, what is your time? That is what I want to
You
hear.
know,
What is
I'm
it that?
thinking, for me, the 4 to 6 is working. So
What? Come again.
For me, I think the 4 to 6 is working. So we can rest.
4 to 6.
Yeah.
Okay. So we have 12 to 2 and 4 to 6. Who
I
again?
would suggest 6 to 8 because some of us are ladies and will be cooking at that time.
So maybe 12 to 2. 12 to 2.
Okay,
Good
we
idea.
have 2 votes for
Yes.
12 to 2 and 1 for 4 to 6 and 1 for 6 to 8. Who else? Michael. I can see some Michael.
Yes, please, I want 6 to 8.
6 to 8. So 2 votes for 6 to 8 and 2 for 12 to 2. Who else, please?
I also go for 6 to 8.
Let's be quick about this.
Hello, Castro.
Okay, that's Kujo, right?
Yes, please. Yeah, Kojo.
Okay.
Please, I want to come in. If you are very observant, so that when it gets to night around 6 to 7, the network becomes very bad. So let's consider that. If you are very observant, that most of the evening, until the time gets to around 7, then the network becomes very bad. So we should also consider that before we choose the 6 to 8.
We are just voting. So the time you want, you vote. That's why we are voting.
Yes, please.
Oh, no, not the time. But we also look at when the network will be okay. When the network will be okay.
That's true.
Network is very bad around
Yes,
that.
please.
That is why me, I don't have any problem. Just that
I agree with George, but I think Felicia is the one with the problem. She has to cook around 4 to 6. So why not
Brother, and solo.
so let's make it 2 to 4. Then from there she can go and cook. That's all.
So I shouldn't cook on Sundays.
After 4.
All right.
Yeah, after 4.
So listen. So for now, what I'm having here is I'm having 2 with the most votes. So that is what I'm going to put in the group. I'm going to put it at the physics major personal science group. Vote on it. By the end of the day, I should have the votes. Now 2 is 1 is 12 to 2, and the other one is from 6 to was it 6 to 8 that had?
No, 2 to 4. From 12 to 2, then 2 to 4. Let's take the 2.
No, it was 4 to 6, not 2 to 4. It was 4 to 6. 4 to 6.
12, it was, and then 2 to 4.
No, Felicia said we're cooking around 4 to 6. And I'm saying that
these are the 3 options that people voted or people commented on. 1 is 12 to 2. The second one is 4 to 6. And the third one was 6 to 8. And we got majority voting on 12 to 2 and 4 to 6, I think. 12 to 2 and 4 to 6.
No, that's true. It is 6 to 8 that got majority. So let's vote on the platform. Just that.
Okay. So it was 12 to 2,
12 to 2 and 6 to 8.
6 to 8. So those are the 2 that I'm going to put in the group. Please, we should vote for 8. That is why I'm saying that it is 2 options that had the most votes so far. I mentioned it. Some talked, some didn't comment. So those commented on are the ones that I'm picking. That is how I do my work. So these 2 options, I'm going to place it at the physics major science group. Okay? Please, let's vote on it there. By the end of the day, whatever vote, even if it's 1 vote that I have, that is what I'm choosing as the final answer. Yes, please.
It was only 1 person who said 12 to 2. Only 1 person.
No, the 12 to 2, we had it earlier. That is why I'm maintaining that one. Majority there were about 10 people there. And most of them opted for 12 to 2. That's why I'm maintaining that one. I hope you get me.
Hello.
So this new development is what I'm adding to it. Yes, please.
Hello, Castro.
Yes, please.
I don't know, but I beg to differ. If you all agree on the 6 to 8, network will affect us. We all know. So if you are you going to say that majority opted for 6 to 8, so we should go with bad network? Let's analyze
But
it.
please,
It's not
that is
about
what majority
no.
voted.
Majority.
So if majority vote for
we'll
it,
vote against them. Don't worry, we'll vote against them. Don't
If
worry.
so if
We'll
majority
vote
vote for it, and then the network is bad too, we should go with the bad network
Guys,
and
don't worry.
majority.
I'll vote multiple votes. Don't worry. Right? Don't worry.
That is
I'll vote
why
against this year.
if majority are
De
voting
Castro.
for that time, that means they're okay with that time.
De Castro.
Yes, please.
Please, there will not be any need for putting it there for what do you call it, voting. I called Sir Emmy. He said from every Sunday he will only be available at 4 to 6.
4 to 6.
4 to 6.
I'll talk with him.
Okay.
Because if you have to listen, if you have to divide it, he himself was going for opting for us to also divide it. So if you have to divide it and he's doing it for us, he must at least make some time for us.
So he said 4 to 6 every Sunday. He's okay with it.
So I'm saying that I'll talk to him if people want it around 12 to 8. If it was supposed to be a certain time, I think you would have. If it was supposed to be on a time schedule, he would have done it. So if
not that we are appealing to him to do that on Sunday for us. So what the time that he'll be available is what we have to choose. We don't have to impose time on him that he's not comfortable with it. Is my suggestion though.
And Castro with the vote. What if Castro? Hello, boss Castro.
Yes, please.
If we go by the voting, so people will vote severally. So I beg, let's agree here and just go by it. Fine. I beg, let's agree here and let's come to a consensus and go by it. Will only be 3 weekends.
You can only vote once.
Only 3 weekends. How would you know? Me, I can vote, change my name, vote.
Yes, that is why I told
change
him.
my name and vote.
I told him that time. I told him that we concluded
send me his number. Send me his number.
I will send it to you. I told him that we concluded on 12 to 2, 4 to 6, 2 to 4, and 6 to 8. And he said he's okay with the 4 to 8.
Actually, the truth of the matter is
this thing I said so. People are not actually so many time at this time. So who can hear?
Because we can vote on a time and it will not suit him.
At least we should who's a teacher they can say the and having a student to can say 4 to 6.
No. If you say that is incorrect. As it has been the issue for many of the lectures, but I was able to talk to them and they were able to change the times. Do you get it? So it's just about how you communicate with the person. If majority are not going to be confident with that time, and you the teacher saying that you only be confident with that time, you can't meet an empty class, and that lesson won't also take place. Do you get it? So what we should do is just talk to him and see if the majority wants to. If majority are okay with the for every time, make them okay. If majority are okay with the 4 to 6, then that will be okay. But if some people want to change it to a different time, that will be okay for them. I think we can still talk with him about it.
We are here, class. What time are we okay with that, or we should change the time? Simple.
Yes. Are you okay with
but
the
I want also when we're doing it. 4 to 6, no, you're okay.
I have no problem since I know
And now you have to see us again. Madam.
Brother, I will be cooking, but on his time will be so I have no option than to abide by his time.
Okay. So you agree you like the positive.
Pardon?
Okay, so are you okay with that?
Francis, I
will try and cook earlier than that.
But you might conclude. I think that one of George.
His number on the platform, on the personal platform.
George, I think George Pejanis. George Kasana.
Benjamin.
Oh, Benjamin.
Okay.
All right. So my final, please.
Yes, mommy.
Hello, this is my final, my final inquiry to members.
Yes, sir.
Are we okay with the 4 to 6?
Yeah, we have no option.
Yes, you
No, it's not about no
Okay,
option.
but
Are you
I
okay
don't
with
know
the
let's
4
to
to
be young
6?
so.
Are you okay with the 4 to 6? That is the question.
Sir Castro,
Yes, please.
we are meeting for just 4 weeks. The
Yes.
lecturer said you meet us as 4 to 6.
Okay.
That's all. For me, end of case. Why?
Okay.
In 4 weeks' time, this whole burden will be over. No be a why? So to me, let's just end it here. Papa, let's say 4 to 6. And end of discussion. 4 weeks per then we are free. Why?
So that's the question I'm asking. Are we all okay with it? If you're okay, please give a thumbs up. Okay.
I am okay.
All right.
We are okay. We are okay, sir.
Okay, Alfred. I can see Alfred. Alfred, are you okay?
Yes, please. I'm okay.
Okay.
Benjamin, your hand has been up since,
Ah,
but
who's
then you are not
Benjamin?
talking.
Benjamin, I'm not talking. Benjamin, talk.
Okay, so I think we are mostly okay. So Alfred is okay. Benjamin, are you okay with it?
Oh no, Clement, say wapeja neza na wadau.
Clement, are you okay with it? Clement.
Yeah, I'm okay.
Okay, Francis, are you okay with it?
Oh, I'm okay.
George, are you okay with it? George Kote, are you okay with it?
Yes,
All right. John Biden, are you okay with it? John Biden, don't call you okay with it?
Wow.
All right, Kujo, are you okay with it?
Me trying.
Caps, are you okay with it? Caps. Mark, are you okay with it?
I think they are watching.
Mark.
Obia peja neza so wada.
Nana Kwame, are you okay with it?
Yes,
okay, then Solomon, are you also okay with it?
Solomon, wadao.
Solo de wada da.
All right, so I think majority here are okay with it. So the time has been decided. Sundays from 4 to 6. Sundays from 4 to 6. Please, let's all be our brothers keepers. I might forget to post the link. Please, let's be reminded to also post it. Okay? I might forget. It's not only me.
Yeah.
So I hope that we will be using the same link for all the lectures. That is the same link that they have assigned for each of the courses. Okay? So please, when it's time, I will post it. If I forget, let someone else also post it. Thank you for your time and have a wonderful day. Goodbye.
Please, colleagues, I said that I've created a personal group. If you are interested, you just join and see what it is about. If not, you can leave.
Okay,
Yeah.
okay.
Hello, Sammy.
We'll be joining. Yes, we'll be joining.
Hello, Samuel.
Sammy is gone.
So I cannot be your call.
Let's pray hard. Then I'm talking to them so that they'll give us some tutorial questions whereby things will come from it. So I'm still talking to them. For the two teachers, I'm in good terms with them. So yeah, I'm one part there. I'm back on
I saw that you wrote to this thing. You see, the last time you sent me some link on the email.
Yes.
Yeah. If you can write to them again about it, okay? Then let me have the questions. All right.
Which one? The questions I gave it to you.
Yes, that I sent it to the groups.
Yeah,
if you can have it
this
early.
week a little bit. We are packing, so I'm a little bit busy. So next week I'll request from the woman when he sends it. I'll bring it to you.
All right then. You're welcome. Thank you. Sorry. Thank you. All right. Bye bye, guys. Have a wonderful day. Mom, Mom, dance, Mama, dance, Sunday. Yeah.
We have to start with the group studies because some of us are not getting time for the lectures. You have to help us.
You start. Last semester, last block, then easy. But this year, I will start. Okay, that's why I think Samuel is trying to also start the destiny now.
Okay.
The groups, so please join and let's do the discussions. Okay. And please remember, Doc wanted us to send the list of all those doing physics and chemistry. Please, for your course, for your centers, please tell them to send me the names. Okay, I'm begging you.
Okay.
All those doing physics and chemistry for your various centers, send me the names so that I compile the list. I beg. Why?
For me, it's only me, so I'll send you my index number.
Oh.
Hey, which center is that?
Yes, Antoine.
But yes, I'm good.
Kaswa.
Kaswa, it's only me.
I heard a normal.
Sure, normal saying. Hey, yes, Antoine, I couldn't know. My indigenous no yadi. A man from here to do Senewa.
Normal.
As a physics, a man among those who are too poor.
You're too poor. Let the back number center.
Hey. Yeah.
Hello. Castro.
Yeah. Nana.
Na me come as we na say mbetimi aboa ya won ho awai. Why social science for no movie school I'm starting so no. I'm BA social science. Na major na matter so e be geography.
Yeah.
Geography, mathematics, economics. Number 2 BA science pa.
For this, I think they write the major and minor. And I'm on to major and minor.
They don't bring it at all. They only write period in science. That's all.
Hey, that's all.
Out mine. That's how much is the pound.
Because physics number science keke.
I'll inquire about it. I didn't raise some inquire because I won't hear.
He requires science. So
social science, economics. If you are joking,
requires science.
So science people what is it? Because so second work plan. In fact, what about whom they? Near control BS science, control BS second one after third class. As a near they want to cry.
Oh yeah, you have.
All right. Okay, so I'll talk to them and see. I see what happens. Okay.
So I'm finding
I'll talk to them and see what happens. Don't worry. Okay.
So last year for I'm sure BS science.
BS science and
BS physics. Because physics.
For you for your practical, some case on much also a BS science. Ọmụ ya wee no ya finding out them na yehu ya nti I think then na ya kese nko mo fa ya major mbra but
why not physics? BS science and then emphasize on the major. It's BS physics.
They will not even write BS physics. They will say BS science.
Yes,
BS
science. Brackets.
Science should be bracket.
For
so
the right.
BS science bracket physics and chemistry or physics. Simple.
They may physics should be physics.
Chemistry.
BS science is food and nutrition is here science.
So they should do. That is what I somebody told me. Those who completed last year. Something last year, they only wrote BS science.
That is it.
So anyway,
Castro says he'll carry on. So let's hope we get something positive.
I saw one who did the economy, home account. So they wrote BS into bracket home economics. That's all. Then the major are the home economics. Other food and nutrition or clothing didn't come.
But it will be geography accounts or geography mathematics or
What you know, accounts and geography what wrong, but then you could say yes, so it's a one yet.
maybe yeah, you will bring your electives and then
No,
your minor.
they don't even they say beard in science.
It itself, me, I've been hearing that the duration no cry an issue to some people. So if you also want to make it blur in terms of percentage, I don't think it's fair.
That is
writing beer science say it's not fair. This idea and I'm saying no, it's not fair. So please cast.
Because when you pay the fees at the bank, the receipt that they'll give it to us, it was written on it, the program Beard in Science, Switch. Beard in Science, Switch.
No, they'll bring the switch. As for the switch,
no, but if as for the switch, even if it doesn't show, or even if you don't write it, the duration for the course tells it. You understand? Because it's 1 year duration. 1 year duration. Everybody who is aware of this program knows that it is only switch that is done within the 1 year.
No, so if you look on time, if you look on it on the 1 year, 1.5 year, yeah, on the portal. So the admission starts on June 2024. May, June, that is what's on the portal.
But even that, it's a degree program within 1 year, 1.5 years.
Auntie Felicia. Auntie Felicia.
Hello. Hello.
Auntie Felicia.
Hello.
Hey, is she gone?
Yes, George.
What I'm saying that after the switch, they will not indicate it. And the year to the program that you do, they don't indicate the year you started.
No,
the
but
year you end
on your CV, you put it there. You started this year and ended this year.
No, if you want to put it on your CV, then you don't need to put it there.
The certificate they are going to give us won't.
But are you sure the certificate will not be on the certificate?
The year. What I know is the year of completion.
Wait, I did my first degree there. Nothing was syndicated. It was distance. It's not stated on it that is distance. So this one too, it will not be stated. And the year two you started, the year you started to will not be written. Only the year you graduated.
Yeah, it is. Yeah, so only the year that you graduated. That's what I know.
So if somebody asks you and you go and tell the person that you did it for 1 year, it is up to you. And then the year really doesn't matter. It is what you can deliver.
I understand, but you see some people and they are. I understand, but you know, who said this issue came up when one time Dr. Peter met us on some, general perspectives of the course. That this issue of like they are using the duration of the program to value.
It's very true. It's very true. Some has when you go and they realize that this is what you did.
Yeah.
And it is covered only 1 year. They will be skeptical about accepting you. Yeah.
In their mind,
it's very true. That one is very true.
I understand what you are saying.
But George, I understand your point. It is up to you for you to go and explain to them that I did it 1 year or not. Because here, the year you started will not be. The year you started will not be on the certificate. It is only the year that you ended that will be there. So there's no need for you to go and explain things to them that I did it for 1 year or not. Just do it. That it's a distance course.
It's a distance course, and you are because that's others. Those who are doing it the distance to their certificate and their own will be the same.
So you just indicate.
Yes.
And you want to state the duration.
Yes. And secondly, this thing. And with this thing too, don't you know that our own cry because we have done other degrees before we are coming. Just that we don't have the freedom to, or we don't have the time to do another 4 years. But I don't see any difference between what you are doing.
No, the thing is there shouldn't be a problem at all. But you see, some people you don't understand where I'm coming from. Some people are narrow-minded, and that is how they look at things. They are myopic. So whatever you think you have, that is not what they are looking at. They have their own weird way of interpreting and looking at things. That's the point.
Okay, I get you.
So you have to tell the person use the degree to apply. That is what you were given 1.5 years as 3 semesters.
Yeah, it's true. All right, Charlie. So nice day.
We are starting the first one at 2 to 4, right?
They say 4 to
4
6.
to 6. 4 to 6 today. Okay, so let's go and rest more. We'll come back.